알겠습니다. Good afternoon, everybody. This is a room for track C under the theme of AI for science. It will be starting in a minute, so please be seated. Please make your way inside and take your seat, please. And also, in the meanwhile, I would appreciate if you can turn off your mobile phone. Maybe I need to do myself first. And before we start. Okay, so it's 1:30, so we need to get started. So good afternoon, everybody. My name is Jong. I'm from KAIST AI, and it's really great, my pleasure to serve as a chair of the track C. So this session is AI for science, and today we are pleased to welcome leading researchers and industry experts who will share their latest research and insight into how AI is advancing scientific discovery. So I hope today's session will be a very fruitful, lead to the very valuable insight and the fruitful discussions. So, and also this session is being live streamed on the official YouTube channels of the Global AI Frontier Symposium. Okay, so let's start with our first keynote speakers. Let me introduce Professor Myuhng-Joo Hwang. He's actually giving a keynote talk presentation about the research agent. Professor Myuhng-Joo Hwang is a well-known and for world-famous researchers in agentic AI. So, and also he is leading a startup company in this theme as well. So please, please give him a warm round of.
Good afternoon, everyone. Yeah, so today I'll talk about research agent from AI research to scientific discovery. So what is research? So everybody here is a researcher, so you obviously know what it is. So research is an iterative cycle of coming up with a hypothesis and validating that idea through experiments and like a literature study and refining the idea over time. And when you finally come up with your manuscript, right? So it's going to be reviewed through multiple rounds of reviewing processes, right? And what survives this rigorous process becomes a publication, and ultimately transforming into papers, patents, and products. So there are two different kinds of research problems. The first is an open-ended discovery. So the goal here is just coming up with new ideas, novel ideas. So you are uncovering the question from a given domain. So you are doing the exploring, right? While the goal-directed optimization, you need to deliver the answer. So you are solving a well-posed problem here. So for open-ended discovery, like coming up with the next architecture for transformer, so that's kind of an exploration problem. Exploitation, you wanna come up with an optimal MOA design or optimal drug that binds to a target protein. So a research agent can be optimized for two different types of scientific discovery problems. So it's an autonomous system that's designed to drive the entire research lifecycle, from the ideation, the hypothesis, right? Planning, validation, observation. And after going through all of that, you are going to revise your hypothesis based on the observation you get from the validation, right? So you iterate through this multiple times and accumulating useful knowledge and confirmed hypothesis, and then write up the paper and get the final result. Okay? But instead of just making this to be fully autonomous, so it would be better to have the human in the loop, because there are many different failure modes, such as hallucinated citations, or just AIs coming up with naive or duplicate ideas. Sometimes the experiments are broken and methodologically not rigorous, and you have multi-agents discussing over a topic. They will just try to just echo chamber, right? So you need to have a human in the loop to guide the direction of the autonomous agent. So the goal of the human and the agent could be focused on what they do the best. So the humans ask questions. So coming up with the novel ideas is what humans do the best, right? And then given a problem, right? The agent could come up with multiple hypotheses and multiple solutions, right? And the humans can just pick one, and the experiment part could be just done by the agent mostly autonomously, right? And it can do basic analysis, and humans can provide the feedback on the insights on what direction to go next to continue with the iterative process. Okay, so the research agents could be very different from one domain to another. But for AI research, because AI research runs entirely in code, so we can just come up with a big, fully closed loop with no real-world steps, except for maybe physical AI. Right? So so we can build a fully closed loop with from the ideation to implementation, which is done in code, and experiment that is also done in code, right? And you can also evaluate the model on benchmark data sets, right? And then write the paper, and then do the reviewing process, like what we do in the just conference venues, right? So this is so we have done some research on this. First, focusing on the generating the research proposal and implementing the code, and fully experimenting and full experimental validation with APIs that are delivered as the final result. So the first work, research agent, is focused on writing a research proposal. So instead of coming up with a novel idea, so what it does is it needs an anchor paper. So given a core paper or an anchor paper, it makes use of the citation graphs to find any papers that are relevant to the core paper. And given those core papers and the relevant papers, we extract some keywords from those papers, and then use a co-occurrence matrix to come up with new entities that are not included in the core paper, but may be relevant, right? And then use those entities and the relevant citation to come up with a proposal. So those are generally using the prompt by the prompt, then with some human guidelines, and those are then reviewed by and refined by the agent by 15 different criteria with 15 distinct agents. Then we iterate this process multiple times, but the performance is mostly saturated after 3 rounds. So the generated research proposal contains the problem and the method and the experimental plan. So it's not a full research paper because there's no experiment that is done, but it's reviewed by these three different aspects: problem, method, and experiment, by 15 different criteria. And those criteria actually comes from the human alignment, right? So we first ask the human to review some of the papers based on these 15 different criteria. And based on the criteria, the GPT, the LLM regions what kind of rubric they should generate in order to reach the same conclusion as the human researchers. And that is injected to the reviewing agent. So the reviewing agent go over multiple rounds of reviewing process. And after about 3 rounds, so we obtain diminishing return. But the refined results, this research proposals look sharper, and they contain more novel ideas, and the methods were more valid. So these are the results. So because there was no other work that tried to write up the full research proposal when we first came up with this work, so we just compared against our internal baselines. And there was like a naive baseline that only used the core papers, and then the ones that use also the references that are related to the core paper, and then the final one that we also make use of the co-occurrence matrix to come up with like relevant keywords. So that resulted in better performance based on the human study, and it also is the strongest prior method. It generates the problem definition and method description, experimental design, each with a rationale. So some of the findings from this experiment is that even random knowledge-based knowledge and more capable LLMs come up with a better research proposals, and self-reviewing with a research agent, a reviewing agent, converge faster, and if you have a better source paper, then you can come up with a better idea, but it only ideates. So it doesn't come up with an implementation or experimental validation. So as a follow work, we also made the reviewing part to be much more advanced by coming up with a decomposition scheme. So instead of just using a single query as a review, so we did a query optimization based on different aspects. So first, focusing on the problem. So what are the limitations, right? Second, like method, right? So method-wise, what method exists for this specific type of problem? And finally, the experimental part, right? What benchmark should be used for this kind of method, right? So based on each aspect, we perform the retrieval over relevant papers. And so those aspect-aware retrieved papers are going to be expanded based on the relevance and scoring, and then merged again to form some context that could be fed into the reviewing agent. So reviewing agents are going to contain the most relevant papers to review the target paper based on the problem, method, and experiment. And we can see that results in improved performance over naive method. So after coming up with a research proposal, then we need to turn that into a working implementation. But transforming a paper into code is a very difficult problem because there is high ambiguity. Because human-written descriptions are very noisy and they are loosely specified, so many of the things are missing, and you need to infer some of the details. And it's also the data is under-specified, and there is no like description of the method, data set, or hyperparameters. So they need to match to reproduce the exact results, but in most of the cases, they're either in the appendix or just in the code themselves. And the code should be very long. In some cases, you need to build a system. In some cases, you can just convert an equation into an algorithm, but it depends on the scale of the methodology that you are trying to implement. And there is a dependency between some of the methods that you are building. You need to build one method based on another that may not even be included in the paper, so that you need to only find from some reference source. And so when we try to implement this for the first time, so most of the LLMs generate code by a single path instead of iterative iteration. So the goal here is to coming up with a Facebook repository level code base based on the given paper. So what we came up with is the multi-agent pipeline from planning to repository. So given a paper, for example, given a transformer paper, the goal here is to first coming up with a high-level plan. So this is what most of the coding agents do, like Claude, right? But we go further than that, and we generate the architectural design by listing of the files that need to be generated, and also coming up with the class diagram and the sequence diagram. But just using the architecture itself, it's not going to give the order, exact order on how what needs to be implemented first. So then we come up with a logic design that's going to give you the order of what needs to be implemented first and what needs to be implemented later, right? And then generates a configuration for all the experiments, like the model size, training step, and so on. After that, after the planning is done, then we do a profile analysis. So that means we set a goal of what to implement and how to implement that. And that is done in this analysis step. And then after a profile analysis is done, then we do go on with the coding based on the sequential order that was decided at the planning step. So this is the result. So based on the Facebook repositories, so just by, if you just generate the code from the abstract, the performance is very low based on the actual judgment by the paper authors. So MetaGPT or ChatDev, those are the agentic coding agents that were popular back then, right? So those were not able to obtain the high performance as our method does. So there is no significant gap between our method and the actual code that was written by the authors. And by the replication performance on the paper bench, which is a benchmark that's, that came out from OpenAI, that evaluates the implementation, paper implementation based on the rubrics. We obtained a much higher performance compared to the OpenAI baseline. And it's also much cheaper. So the iterative agent proposed by OpenAI just brute force iterate between the generation of the code and just re-implementing it, right? But our method does very careful planning to the details, and that helps with with lowering the cost in generating the code. And we can also see that every stage helps. So removing any of the step would actually hurt the performance. So it generates the code that's on par with the author's own code. And planning from the top down is better than brute force iteration. And what we can see is that the order is really important and not just the architecture. And the automatic judge was actually very relevant to the human judge performance. It's cheaper and better, and we can actually implement the full code starting from the code base that's generated by the paper coder. But validating an implementation is going to take more than that. So it has to go through experimental validation. So the paper to code generates a code, but it doesn't really do the experimental validation, right? So it just generates the code base that could be further utilized for implementing the given idea, but it stops there. So we came up with the AutoML agent that can do the rest of the experimental validation and generates the deployable API. So it retrieves and pre-processes the data and the model, and it searches and ranks the candidates, and it automatically tunes the hyperparameters and trains the model and evaluates against the spec. So all of them are just done automatically using agents. So the AutoML agent architecture is given here in a higher level. So there's an agent manager that does the planning, assignment, and verification, and decision, and everything. So given an initial request, that it does the request verification. If it's unclear, then it's going to ask the human user again for clarification. So if valid is implementable, then it's going to parse the request, and then the prompt agent is going to optimize the prompt. And retrieval augmented planning, so you use the retrieval augmented planning and get the papers and also a relevant code base from GitHub and archive and Hugging Face. Then at the execution step, the data agent is going to prepare the data, and the model agents are going to prepare the models that are known to perform well on the given task. And then the execution verification step, it checks whether the generated plan meets the specification. So it's actually going over multiple rounds of planning and revision steps before it actually executes the plan. And when the plan is verified, and then it's going to run by the operation agent, which builds the full pipeline skeleton in code. So it actually runs the code. And based on the feedback from the runtime environment, so we're going to do the implementation verification, thus runtime debugging, and finally, we're going to get a deployable model. Okay, so when it first came out, so we compared this against other agentic systems for AutoML and just base LLMs. And what we saw is that just base models, baselines like just GPT-4 or the AutoML and other AutoML agents were not able to generate deployable code. And it is mostly because they don't have this planning and verification and runtime evaluation steps, right? Which makes the code that's generated by our system to be deployable, like runnable, executable, right? And for the harder settings, when given the consent, we were able to generate the code that meets the perfect specification for 87%, while the baseline completely fails. And the performance of the generated model was better than the ones that are built by the human experts. So why does it work? So instead of just generating a very single long plan, so we divide the work into rule-size subtasks. Let's say we have data agent, model agent, and operation agents and verification agents that are all doing their parts. And this was much better than just using a single agent for the whole step. And the rule decomposition, verification, all of that actually contributes to the final performance. And given any prompt style, so we were able to get same results, and it shows that it's stable across different system prompt styles. And for tabular data, it was achieving similar performance to the baselines, but it excelled in training the LLMs for the vision and NLP and graph and time series data sets. And we were able to get the final working API from this. But so far, we are talking about AI for AI research. But this is all done in code. But for scientific discovery, we have to leave the machine. And instead of just doing computation, that you may need to do the simulation that may take hours, right? And maybe do some wet lab experiments to find the ground truth, right? That could take days and weeks. Okay, so what we are doing in this direction is construction of what we call as a knowledge-centric research agent. So we view the research process as an expansion of the knowledge, or the horizon of the known confirmed knowledge about regarding a domain. So what agents do is that it grows a causal knowledge graph and validating the links by either the literature study, simulation, or experiment. First, it come up with a hypothesis, right? So given a problem, it comes up with a hypothesis, and it selects the tool to validate the hypothesis. The cheapest tool is the literature. If there is already some publication that confirms that hypothesis, then our research agents say that this is a confirmed knowledge, and then add that to the graph. Or if there is a simulation available to test the hypothesis, then we are going to run that simulation tool. Finally, if it needs to be confirmed only through the wet lab experiment, then we are going to ask the human experts to do the experiment. So everything that's run, if we get the results of the simulation or the experiment, then all the results are going to go into the causal graph as a confirmed knowledge. And some of the hypotheses are going to be refuted, right? And some of them are going to be dropped, right? Some of them will remain as hypotheses before they confirmed with more rigorous methods, right? And we make use of two units of knowledge, and first is memory, and there are episodic and semantic memory. The episodic memory is what happened when agents made certain modification. For example, if the agent mutated certain drug molecule in some ways, then it's going to record the results that came by that mutation. And then if we have a lot of this episodic memory, then we can consolidate them into some semantic memory that corresponds to some scientific principle. And these scientific principles go into the knowledge graph. Like what happens if we do this kind of manipulation to the molecule, right? And the second type of knowledge is the lab notebook. That is more like a shared knowledge base across multiple agents, where the multiple agents can vote, comment, and just come up with new patterns. And then finally, we have the causal knowledge graph that encodes the actual causal relationships between the confounding factors and the results. And this is used by the world model. So before we started using the agent, we were working on AI-assisted molecular discovery based on like reinforcement learning. So we first started with a reinforcement learning that somehow assembles the fragments to come up with a new molecule. And then we expanded that idea and came up with the diffusion-based approaches that can generate the drug molecules with a single sampling step. And we also came up with a method to generate a sample from outside the distribution. More recently, we were working on genetic algorithms to come up with new molecules, and we generate like 3D molecules instead of 2D molecules. And finally, the latest methods makes use of the large language models to come up with a hypothesis and then apply that to the genetic algorithm. So instead of doing just random search over the population, we do guided evolution. So I'll go into details of that. So this agent has two tools. First is a crossover that can splice the two parents into one. You splice the two parents and then combine them into one, right? That's a crossover operation. It also has a mutation operation. It rewrites one spot, right? But for every crossover and mutation, we have some operator library. And we have some kind of semantic library that are confirmed by its result, right? We do crossover, mutation, and then use the ML surrogate to check the binding affinity between the protein and the drug molecule, right? So that's the cheapest measure. And you can screen many of them. And based on the ones with higher binding affinity, we run them using the docking simulator. And we also can filter them further using FVP or MMGBSA, right? So, which is much more accurate, but more expensive. The most expensive method is the wet lab experiment. So what is stored in the molecular, what is stored in the memory is the molecular knowledge, like what works, right? So like these are like this kind of like episodic memory that when with this kind of crossover and the mutation, we have better binding affinity or any effect they had over the drug molecule, right? And the operator library can give a guidance on how to do the search. And those are injected into the context of the reasoning agent. So starting with the population, the candidate pool, research agent does the breeding and mutation using the memory. And finally, it does the scoring and selects the best candidate based on the cheapest tools the first, right? The ML surrogate and then the docking score. So for every mutation and crossover that is done by the agent, the agent record the effect. Like added like the CL at the aromatic ring, which improved the hydrophobic pocket fit and the score gain of this, right? These are all generated using based on the agent's interaction with the actual molecules, and those are put into an episodic memory graph. Then after we have enough sufficient number of those memory entries, then we're going to run some clustering based on the Tanimoto similarity to find some scientific principle that could apply to many different molecules, some generalizable principles, right? And we can obtain something like this, halogenation on aromatic core with binding. So this is a general principle that could apply to many different molecules. And the agent used the both to come up with the next mutation and crossover. So this is the guided evolution. So what is shown here is that when we consider the average top 100 score, with no memory, the score is very low, right? Using the episodic memory alone significantly improves the performance, and episodic and semantic together results in much better performance, right? But with additional refinement, it gets better and better. So I'm going to talk about the refinement stage in the next slide. So after we do the stress testing, using the principle and the refined hypothesis and principle, we were able to obtain a very high score for the given the same round of generic algorithm. Okay, so when the agent use the stored memory, it does retrieval. So it ranks the past based on the top K episodes that are relevant to the given molecule, right? And then for the context, for the next LLM core, the top K hypothesis and the cluster principles are going to be used to generate the mutation or crossover. And it also refines its hypothesis. First, it comes up with a hypothesis, and the hypothesis may not really work. It may come up with a new observation. So the previous hypothesis that we obtained from the episodic memory may now apply to all molecules. Then it refines the hypothesis that adding the CL helps unless the ring is already substituted. So it's going to apply to only certain cases, right? So what we found out is that agents mostly benefit from failures. So it doesn't really generate good insights from success cases, but more from the failure cases. And also by adding the parent-based re-ranking, by just not using the fitness, but also a molecular similarity, we can improve the performance further. Okay, so far I have introduced some of the works that we have done so far, and these are some of the ongoing work. So we are also trying to come up with a persistent shared memory for the research agent, because the problem is that the research agent's memory are not shared across agents, or the human memory is also resides in the human's head, right? So we want some kind of knowledge base that could be shared across multiple agents, not just by one agent, but by the literature agent that searches over relevant research papers, and hypothesis agent that comes up with new hypothesis, an experiment agent that does experiment, right? And the final agent that does all the paper writing. So it would be good to have all the agents to access a single knowledge base. So what we are building now is a self-evolving lab notebook. So first, agent execute a hypothesis, and it records what happened, right? Not just the surface fact of what happened, but it also does comes up with a reflection and going to come up with the insights on why this happened, right? And some kind of hypothesis, right? So that is later used by other agents. If the other agents find it useful, they're going to upvote that knowledge. If they are confirmed to be not valid, then it's going to be downvoted. So there are like 3 agents that are that manages the lab notebook. First is the reflector that compares the runs and writes the grounded reflection. And we have the curator that promotes the proven reflections into the patterns, and the organizer that just maintains the overall upvotes and link and structures. So if we just ask the agents to write the memory based on what happened through those experimental validation, it's going to just come up with a very weak insight with no evidence path and nothing, right? But we gave the prompts such that they come up with a grounded reflection report with support, contradiction, key insights, and what needs to be done the next, right? In this evidence report, the grounded reflection report gets better and better over time as it is used by more and more agents. So starting as a thin notebook, it becomes an encyclopedia. Okay, so what we are also working on is the construction of a causal knowledge graph that makes the models to enable intervention and perform counterfactual what-if reasoning, right? So just the agentic memory, knowledge graph, lab notebook, everything is good. And they are helpful for the research agent, but they cannot be used for counterfactual inference. To be able to do the counterfactual inference, we need to have the causal relationship between those factors. Okay? So we are building this causal knowledge graph that can intervene and imagine based on counterfactual evaluation that actually removes the cause and watch the effect, right? And simulation, and also by going over the rigorous results that are written by the others, right? So the causal world model is the one that makes use of this causal knowledge graph. So it's not just a knowledge graph, but but LLM augmented with knowledge graph that can reason based by following the knowledge graph's causal structure. So it does the forecast of what's going to happen based on the given scenario using the forecast model and the causal knowledge graph. And what we are also doing is a self-evolving causal world model. So that means the world model doesn't stay static, but agents grow that causal knowledge graph by interacting with the world, like doing the literature study and coming up with a predictive model, right? And using the predictive model, simulation, and the real experiment to confirm that hypothesis, right? To confirm the causal relations between two factors. So the principle here is using the cheapest interaction first, and then going through more rigorous validation steps. And what drives the next probe is the uncertainty about any links between two factors. And we have actually built something similar called agentic plant twin that combines the physical AI, combines the simulator for chemical plant with the knowledge graph and the world model. So the agentic AI does reasoning and acting, the reasoning and careful configuration of those factors. And physical AI mirrors the real plant. So it models the physical activities, right? Like thermodynamics and so. Play. Can you play the video? So this is a final agentic plant that we have built. So it's not just a 3D model, but this is a 3D model that's combined with a simulator called Aspen that does thermodynamic simulation. And also it combines the time series data that's coming up from the live sensor that's installed at the plant. Okay. So another thing that some of my group members are working on is the thing called agentic research twin. So this is focused on the multi-agent collaboration because we believe that research is essentially a collaborative process. So an agent, if we use the research agent over time, right? By all of this brainstorming, discussion, and all the like, experiments that are done by the research agents, it's going to understand our direction, right? And also what problems that I'm focused on. So based on the lab notes, chat with the colleagues, papers that we read, experimental results, and any of the spoken words to the agents are going to be analyzed by the agentic research twin. And it combines, it captures the style and taste and personal knowledge graph, and also captures the privacy on what needs to be what needs to be kept secret and what could be discussed with the others. So the goal of building this research twin is making this research twin to work 24/7, even when I'm not working, right? So it reads new papers, generates new hypotheses, and runs simulations or experimental validations. And more importantly, it talks to other twins by other agents. All of this is done proactively. It's not only doing this job when it's asked to do it, but it's just a perpetual demo, right? So first, we just tell the agent what to do, right? Then this is some experiment, but it failed, right? And the twin is going to add that to the private knowledge graph, so it knows your what kind of topics that you are exploring, right? Then it can match that subgraph to the personal knowledge graph by the other researchers. If you find the match, then it means that you are working on a similar problem, right? So you can find some collaborator through this process. What we are building this for is our lab members, because our lab members even do not know what others are doing, right? But this could be built in like the global scale, right? To foster collaboration across the globe. And we can just let the twins talk, right? Without disclosing sensitive or confidential data or information, right? Okay, so far, I have discussed about research agents, and we have first focused on the AI research, and we have expanded to the application of the research agent to drug discovery. And now we are working at Samsung Electronics to apply that to the material discovery. Okay, so that's it for today's talk. And if you have any questions, then please let me know.
Thank you very much for the very nice and exciting talk. So this is open for one or two questions from the floor. So any question from audience, please raise your hand. In the meantime, I have one question. So for example, this is actually, this kind of agentic framework for harnessing the LLM to actually do this kind of scientific research is a really exciting area of researchers. I mean, groups are focusing on that one. And on the other hand, by utilizing this kind of thing and making system more complicated, it can also prone to some kinds of hallucination from this kind of procedure. So my question here is now, for example, just utilizing this, harnessing this kind of multiple agents together versus having a for specialized big foundation model for specific tasks. So I think there might be two different kinds of approaches for the same problem. So could you comment on what you think is the direction for the future? Yeah.
Okay, so we started from building foundation models that are like specialized for like drug molecules when we first try to build a foundation model. But that kind of approach doesn't really is too capital intensive, right? Resource intensive, and it's also because there are new models that are coming out almost like every month, right? It's better to just focus on separating the knowledge from the model itself, right? So what we are trying to build is a knowledge graph augmented language model. So we have some like base technologies for that, and so that it only follows so we are focusing on memory and knowledge and exporting what agents have learned to be generalizable across multiple different foundation models. Right? Not sure whether that
Yeah. Okay.
answers your question.
Okay. There's another question from audience.
Steve Wall from NYU. My question is, have you thought about filtering when you're talking about your agents for creating research proposals, maybe filtering it by a library of actual research proposals? Like at least in the United States, most grants are what's called foilable, and you can actually get the actual grant application to kind of feed into the system. So my question is if you ever thought about doing that rather than the papers.
I'm not sure whether I got your question correctly, but you were asking whether the reference papers were, yeah.
Instead of just using the reference papers, you can actually use reference grants that have the full proposal, is what I'm getting at. Have you tried that yet, or it might be something worth looking into?
I think that's a direction that's worth looking into. So maybe, yeah. So research proposal could be the one that we could like search for, right? Not just research papers. Yeah, I think that's a great direction to explore.
Okay, great. So any other question from audience? Otherwise, yeah, there's one more. Okay.
This is a quick question. If you have a research agent, will the graduate students need an advisor? And will a professor need graduate students? What makes you a scientist if there is this research twin that works 24 hours, 7 weeks a day? What do you think?
Yeah, I think those research agents are just making us to be more productive. So it's like students advising over like younger students, right? So we can treat the agents as our students or I don't know, technicians or yeah, because in the end, you need to come up with novel ideas and coming up with the insights or verifying what the any of the hypotheses or any of the analysis that are coming up from the AI needs to be done by the human researchers. And you need to be accountable for any research outcome that you generated, right? So accountability and just giving guidance, right? Those are the things that could be only done by the human researchers.
Okay, this remind me one discussion during this morning. This is question for you. So there was a discussion during the panel discussion in the morning that maybe agents shouldn't do any generating hypothesis and human need to do, but an agent maybe need to validate. But anyway, so that means in most of the researches, some people is approaching to generate the hypothesis using AI, or some people think differently. So based on your experience in this area, so what is the most productive and most feasible way to approaching in AI for the science?
Yeah, I think it's just both ways, right? So the AI can come up with novel ideas. So it is in some recent study, there is recent studies say that the novelty that is evaluated by the humans were much higher for the AI generated ideas than the ones that are generated by most humans, right? Human researchers. Like, so what I want to say is that even if we are doing vibe coding every day, right? Some of the programmers are much better than those coding agents, right? So some of the researchers may come up with a more novel idea, maybe come up with better insights than research agents, but maybe most of the tasks could be just automated using research agents. Because something that is more incremental, right, but needs to be confirmed, right? So you need to know whether it fails or not, right? Or whether, I mean, some kind of some problems that humans need not really focus on, right?
Okay, great. Thank you very much for
Okay.
your excellent answers. And I think we need to move on to the panel discussion. So let's thank our speaker again. Yeah, so for the remaining time, so we are going to have a panel discussion till, I believe it is 30:25. So we have a 1 hour left. And please, actual panelists, please come up. Yeah. Okay. So as you see, so we have 4 experts in this area, especially for AI for various parts of the sciences. So before the panel discussion, I actually distributed several questions and then we had some initial communication for that. So we are going to continue that discussion in front of the audience. So the topic I actually gave them, the agenda was, first one is, what does AI for science beyond scale mean? And second one was, what is the key opportunity and bottleneck? And then what should we discuss regarding data validation, reproducibility, trust, and collaboration? That was my initial question, and there was a lot of exciting exchanges about that. So I think we are going to based on that, and I'm going to give some kinds of question to the panelists. But before I give the question, so please, I suggest you to introduce yourself and briefly give some ideas about your view about AI for science or science for AI, and maybe I give you respect.
Hi, I'm Eunok Paek from Hanyang University. I'm working on bioinformatics, not just based on AI, but I develop algorithms too with my computer science background. Actually, I'm an old school AI person from 80s. Leslie Kelbling, who gave the keynote speech this morning, I went to school together with her during my graduate studies. So we're very old people in the AI community with different methodologies. But recent advances in AI made us to look at science from different perspectives. So we are trying to use AI as much as possible to advance science in some sense. Will that be enough? Thank you.
Hello, I'm Eric Orman. My background is actually group theory, and I was a former software engineer at Google who pivoted into healthcare. I trained as a neurosurgeon, and currently I'm the director of AI research for the NYU Langone Health System in New York. I think for me, AI for science is always something that we do a lot in my lab, both on an algorithmic development end, but also constantly trying to actually develop tools that we can use them in the service of life sciences research, which is the mandate for our institution. And I think maybe one of the topics we'll talk about as this conversation progresses, certainly for us in a very highly regulated space in biomedical research, imposes kind of unique constraints on how we develop models and how we utilize them.
Yeah, hi, my name is Donggen. I majored in computer vision. During my graduate school, I worked on a wide range of visual recognitions in computer vision area. And after that, I co-founded a company in medical AI field. So I am working on developing AI model to support early stage cancer diagnosis and cancer treatment. And recently, I'm also working on developing medical specified language model to support better clinical decision support. Yeah, I'm honored to be here. Thank you.
Hello, my name is Dan Lee. I'm currently a professor in the Electrical Computer Engineering Department at Parnas University. I've been working on machine learning and robotics for a number of years, in particular thinking about representations in these neural networks using statistical mechanics, geometrical tools to try to understand what's going on. I'm also visiting a visiting appointment at Flatiron Institute as part of the Science Foundation in New York City, as well as Korea Institute of Advanced Studies here in Seoul. And so I work with a number of mathematicians and physicists who are thinking about, how AI can be used to kind of make basic scientific advances in their fields.
Okay, thank you very much for the introductions. So my first question to all the panelists is actually, we had an excellent keynote talk by Professor Hwang, and it seems like there are a lot of exciting opportunities, but based on your own experiences in working in specific scientific field, what do you think is a current bottleneck for utilizing AI or develop AI for specific field, or just like utilizing AI for your own field? Maybe.
Well, the current day LLMs, I think, have learned everything the humankind has accumulated in their languages. So, I think that LLMs know better than most of us when you think about those knowledge represented in some kind of symbols. Whereas science is about nature. AIs can learn about nature by looking at the representations humans have created, but AI cannot learn the nature in and of itself. So I think in that sense, AI is kind of limited, that they cannot directly observe natural phenomenon and try to discover the underlying principles. With the help of this self-driving labs and lab in the loop approach, it is possible, but the approach itself is limited in the sense that the kind of labs associated with this agent system is built by human, and it is not completely open-ended. So it's a closed system, and AI can only learn under that context. So I think that scientific community has its own standing in that sense, and its discoveries will continue and will go hand in hand with AI advances, but I don't think it will be completely replaced by AI. That's my personal view.
Okay, great. So your view as a
Yeah.
AI scientist.
Well, also I think as a health system executive, and really maybe this could be my hot take, but I think one of the biggest problems right now are actually benchmarks. In some ways, even the very existence of benchmarks as we use them in the computer science community. And they're wonderful. They democratize research, they standardize research. We spend so much time optimizing on benchmarks, but I think increasingly we're realizing that there's a enormous, in some cases, gap between benchmark performance and real world performance. And as soon as we start optimizing in some ways to drive benchmark numbers up, they cease to be valid measures of why they exist in the first place, which is to measure some kind of real world impact. So I think that gap between benchmark performance and real world performance is increasingly a major problem. And also in the spirit of that, especially when I think of our health system, in some ways, even if we had the benchmark, which we perform phenomenally well on, and even if that benchmark was perfectly correlated with universal real world performance, in some sense, for our institution and our business, we don't care. We want it to work well for us, which is potentially some subset of that benchmark, which maybe it's not working out, but it gets washed out in the average. So I think really the current way we build benchmarks in some ways is one of the biggest barriers to progress.
So,
Yeah.
maybe especially as a businessman, you may see some kinds of bottleneck to monitorizing it. Yeah.
Yeah, I
Please.
totally agree with Eric. I think there is a certain gap between the current success of AI model and the actual impact. Here, the actual impact means the real actual scientific discovery. I think this gap is caused by two parts. The first one is rigorous validation, and the second part will be explanation. If we, I think it is time to invest our more energy to design and conduct rigorous validation of the hypothesis that AI generates, because the benchmark itself would contain a lot of compounding factors and bias. So it will need to design a very ideal and rigorous validation scheme and conduct that validation. And depending on the validation results, then there will be many factors that causes the failure. So it is time for us to take that result or feedback and redesign our AI model to closing the gap between the benchmark and the real world. And second, it is also necessary to enhance the cross-domain collaboration to enhance the ability to explain why this result came out. So in short, I think the main two bottleneck would be the explanation part and also the rigorous validation part.
I can add something too. So, I think the lesson that we learned in machine learning and AI is that, with scaling, the data is necessary for good scaling. A lot of these domains, we don't have that much data, so obviously these work on automated data collection, lab in the loop kinds of procedures. But I think if you look back historically at the greatest scientific discoveries, they were made with actually very little data, empirical data. So if you look at kind of Einstein's theory of relativity, there's no data on saying, how space and time should be integrated. Or if you look at the discovery of DNA molecule, right? If you look at the X-ray crystallography data at that time, it was extremely poor. And so really this kind of intellectual leap that great scientists make, I think still is lacking in terms of what we can do with AI.
I think this is a really important point. So that means most of this current AI for science researchers is more like a data-driven. It's like having more data-inductive biases, but we need some kinds of top-down insight of this kinds of scientific problem solving. But so then that leads to my next question. So, do you think it's possible to imbue those kinds of insight to the AI itself, or that's actually not possible in AI for many years? So, what is your thought on that?
I can start with this and other people can join in. So I think it's interesting because we're kind of at a crossroads in machine learning. So if you look at kind of one end, Rich Sutton said the bitter lesson of AI is that you basically don't want to build in any kind of inductive biases or domain knowledge to be able to make AI just learn kind of tabula rasa, and that's the best approach in a lot of domains like object recognition, speech recognition, language models now. There's no prior notions of grammar or how form and picture made or anything about, you know, geometry of images, object formation. That's all gone. But now in science, the question is that recipe still going to work, or do we still need to build in better inductive biases that humans have about these fields in order to make them perform? And I think that's really, to me, a central question, is that this kind of traditional conventional recipe in machine learning of just forget about all your kind of prior knowledge and just make something work with data, or are we going to have to use human expertise and domain knowledge and build them somehow into the network themselves and allow them to learn better knowledge discovery? I think that's.
I was maybe to follow up on Dan's example of relativity, you know, and maybe you can push back on that a little bit. Like in the Einsteinian thought experiments that go into that, there actually are some incredibly rich priors driving those experiments, just that presumably Einstein encountered by being human and living in the world and seeing how things relativistically relate to one another spatially in terms of motion. So I think there are a lot of critical priors like that you know, we as scientists encounter by being humans and living in the world that we maybe take for granted a little bit, in part because they're so abstracted. And I do think that Professor Choi's work with the knowledge graphs is making some very cool strides towards that. Yeah, I think that those abstract priors that are really missing from a lot of the models, and I think lead to what I think, at least my personal experience with kind of AI scientists right now, is that the hypothesis generation really is one of the big shortcomings.
Well, let me push back on the relativity example. So, you know, obviously at that time, there was a lot of examples of Newtonian relativity, right? Like running after a train. But I think what inspired Einstein was his thought of how you could catch up to a light beam. And that's where the domain, when you get to near the speed of light, is when things completely break down. And that's where he had to use some real kind of intellectual leap to figure out how that's connected to electromagnetism. That was really the insight.
Do you have something to add on?
Yeah, it reminds me of the success of AlphaFold. It's not just the data that, I mean, it's the data, but it's not just the three-dimensional structured data that that derived the success of AlphaFold. It's the huge amount of sequence information that's been restructured in terms of multiple sequence alignment that sort of extracts the sequence patterns out of the similar proteins. So that kind of prior knowledge, I think, is very important in AI for science. And also it reminds me of a paper just published in Nature a couple days ago. It's about building a virtual yeast. The entire organism can be modeled using AI in 5 and 10 years from now. It's a perspective paper on this long-term project to build virtual yeast. Their catchphrase is biology first. It's not data first. So biological, prior knowledge and some mechanistic models involving metabolism of yeast, that will help AI to learn fast and also guide it into the right direction. So I believe it is very important to use this kind of prior knowledge to build AI and to verify its performances.
I think it depends on the two factors. The first factor would be the area of science field. And the second factor would be the level of the prior knowledge. So let me first look at the area in the science field. I think there are some area where we can get access to huge amount of the data. For example, coding and algorithm or mathematics, something like that. In that kind of field, we can access to huge amount of the data for a model just to get learned from that data. But on the other side, there is some field like medicine and biology and chemistry or material science. There requires a lot of investment for the rigorous validation. So in that kind of field, I think it is still necessary to utilize inductive bias and prior knowledge. And also for moving to the second factor is about the level of prior, I mean, level of evidence. If on prior knowledge is well established and fully validated and unquestionable, then I think why not we use that knowledge? Why not we inject that knowledge to the model development? I think rather than excluding that, if we can utilize those kind of prior, then I think it would rather improve the model generalization ability, because it can clean up some unrelevant correlation in wrong data. So I think it would be depend on the area and the level of the evidence.
I see. So I may be more provocative than yeah, because actually, for example, among the science field, most human prior dependent field could be mathematics, I would say. But even in that field, I saw some news article that Google DeepMind solved a very long-standing unsolved math problem for many, many years using the AI. So those kind of things is currently being actually unfolded right nowadays, right? So given those kinds of parts, so then what is actually, I'm trying, yeah, I don't have an answer, so that's why I'm asking question. In those kinds of like level of unexpected level of expertise in AI. So I'm trying to ask questions so that what is the role of the human and AI in the loop of AI for science or science for AI in this kind of human in the loop pipeline? Do you have any thought on that? Yeah.
Well, the difference between the coding domain and natural science is that with natural science, there is this underlying principle that governs the nature, whereas in the coding domain, there is no such so-called principle that governs the coding behavior. So I think that's why we think that when we're dealing with natural science, we have to be more dependent on the observations we make, this objective data, whereas coding is a lot like language, just text, right? That's expressed by human. So I think there is this fundamental difference between two domains. And with the mathematics example you just brought up, I think the difference is there the problem is well defined. It's the matter of solving it. Although it needs a lot of imagination, I agree, but there the problem is very well defined. In science, humans' job is to come up with a good question, which is defining the problem itself. If AI can start to define a very interesting problem in and of itself, yeah, then the world will just disappear. Maybe we have no reason to exist on Earth, maybe. But I don't think AI has reached that level of creativity to define a very well-posed scientific problem on its own. So I agree with Professor Myuhng-Joo, who said that, oh, don't try coming up with this hypothesis generation thing, and that's why I agree with Professor Cho in that respect.
I think I agree with your insight about, yeah, in the mathematic problem, problem is even the AI could find a way in anyhow, but your point is defining problem itself is the most important part for human can do, right? I see. Okay, that's a very important insight. So do you have anything to add? Please.
Yeah, I think in the math domain too, they struggle with the fact that like the proof, the OpenAI result on the Zerdos conjecture was actually a counterexample to the conjecture. And actually validating a counterexample is much easier than validating a proof, right? And so the mathematicians struggle with AI generated proofs because it comes up with something, but do you really believe it or not? And some human has to go in and actually check every piece of it, which is very difficult if these AI proofs are basically pages and pages long. So this is really a bottleneck, is the kind of validation verification step, which I think is also very important in science, where you have or health, where you have life critical kinds of results.
Also, maybe to follow up on the unit distance problem point, and maybe this is one of the positive parts of AI, is that a lot of human mathematicians assumed that it was true and weren't looking for counterexamples, whereas it took an AI which maybe didn't have that prior, that bias, to say, wait, let's look for counterexamples and find them.
Okay. So I think during the initial question, actually, many people, and also during the discussion, many people said that in this era of AI for science, that collaboration across the multiple lab and also data sharing is very important. And also Professor Myuhng-Joo also mentions about these kinds of automatic twins for the collaboration. So I think, yeah, that I believe everybody is agreeing with that one. But there was a question from Professor Beck during the talk, and also I had the same question. But during these kinds of necessary need for the collaboration, and what do you think is the role of the graduate student? Because actually, it seems like many things can be done. Many of the research can be done automatically. And even I noticed some professors find that it's more efficient to use Claude Code or other things rather than asking students to do that. But what do you think as a professor is an important part of collaborating with your own graduate student? And also, if you are undergraduate students, I think that has the same question in the morning. What do you think they need to learn from this period of AI evolution? Anybody? maybe you can say.
I can start. I mean, I think professors like to use AI because they answer you within a minute after you ask it a question. Whereas graduate students, they go away for the weekend, and you're like, what's the latest result? And so I think there's a difference in response time. But definitely, I think I agree with Leslie Cabling this morning when she said that what she looks for in graduate students is for them to surprise her with something that she hadn't thought about. And in some sense, AI doesn't do that yet, right? Because you're prompting it, right? Whereas I think the spontaneity of what graduate students or postdocs come up with is, I think, what is really the core of kind of scientific advances.
Yeah, I completely agree with that. I think that the creativity that I think we all think is such an important part of the hypothesis generation science, which that can emerge from both being incredibly knowledgeable of the field, but also a lot of that can emerge from being not knowledgeable of the field and willing to ask questions that you don't know why the question is crazy. And I think some of the best science, at least for our group, I know, has come from students who, not knowing how many people tried this and failed, said, hey, let's do this. And then we tried it again a slightly different way and got a really surprising, very cool result.
Yeah, I completely agree with you. I started to do research in bioinformatics as a computer scientist. So my knowledge about biology is very, very limited. That was, I think, very good thing for me because I have no reason to be shamed not knowing about biology. So whenever I don't understand something about biological field, I have no reservation whatsoever to ask questions. What is this ABC in your work? So I expect the same thing from the students. They are here to learn. So it's natural for them not knowing a lot about the field. So they are very, they are allowed and they're free to ask any questions. So it is very inspiring to get this, fresh questions that we assume to be always true during our, academic career. But then these fresh people come up to me and ask just very groundbreaking questions sometimes. Why should it be this way? And that's the pleasure of working together with graduate students, I think.
Maybe Dongwon has a different kind, maybe similar or different kind of view as a two-person learning companies. So maybe
Yeah.
you prefer the AI employer, or what is the difference between them?
Maybe professor can push a student to get things done in the right time. I think it is also important. It would be more important for professor to solve a bit more philosophical and fundamental stuff. Like, I do believe a good leadership would not be like micromanagement, but a good leader would make some people fully motivated and help the people set very high bar for their work. So still, I think this kind of very fundamental stuff cannot be replaced by AI in the future as well. So yeah, this is my view. Thank you.
Yeah, I think you have a very important keyword, the motivation. So as a CAIO from big companies, and in this era of AI, then how can you motivate your employees? Yeah. I think the same goes to other professors, how to motivate your students.
So very difficult question to me. So actually, I try to explain the real value of the work that we are doing. I mean, how can I say? I do believe a good engineer and very high quality, high-end engineer tend to have, how can I say, the tendency that they become more motivated in the value rather than something quantitative achievement. So as a person working in medical space, medical AI space, I try to deliver my thoughts in the way to explaining the value for, we are doing something for humankind, yeah. So that's one of way for me to motivate people. And second would be creating a real impact. So whatever you do here would be looking very minimal, but once we reach to a certain point, then it will actually influence the real world. So that would be can be a good motivation for them to take this hard time. Yeah.
I see. So how about you, Professor Beck?
Well, I think there are various types of professors to the graduate students. I'm more like a coach style. I don't give them directions where to go or what's the correct way to do it. But I always sit down with them and we look at the same direction. What do you think about this? And I always send them various publications that's related to their research. And I make my students to choose their research topic on their own. I never give them, oh, it's better for you to do this kind of research or whatever. It's their choice of the topic. That's what I learned from my advisor, Professor Niels Nilsson, who just let us just doodle for like almost 2 years to come up with an interesting research topic for PhD thesis. So that's what I do with my students. I allow them to do whatever exploration they want to do, and they can come up with their own research topic. But then I sit down with them and review various articles together and suggest them related research topics, etc. So I think students, if they come to the graduate school, they're already motivated to a certain extent. And what I need to do is just feed them some materials to keep that motivation going. I don't really have to, put a fire on them, but they are already a ball of fire in a sense.
Oh, that's a good point. So even with the era of AI for science or research agents, still those kinds of one way of motivating is still working. That's the point. Okay.
Hopefully.
Okay. Eric, do you have any thought on that?
I think we have similar teaching styles. Also, I'm sort of the coach. Over in my desk, it says, build things that save lives and understand intelligence. And I always tell people that those are the two missions of our research group. And if you're not excited by that, A, I find that odd, but B, like, go do something else that you find exciting. I do think too, though, maybe especially the modern AI era, especially as a professor, the other part of that coaching, though, is helping students, I think, face the maybe at times what feels like an existential crisis over the resource gap, which we heard some talk about this during the general scientific session. I think a lot of times they see these massive labs throwing $10 million into a single experiment. And I think it's a role of motivating students to show how science doesn't have to be that way and can be just as exciting if you're all the ways of dealing with kind of that gap in resources or finding the resources that they do need to be successful in other ways. Maybe it is computing, maybe it is access to data. But I think to me, that's maybe the additional sort of modern concern that we have to address as faculty.
How about them?
Sure. I think when you look at kind of scientific research, and I think as graduate students, we learn we have to get results. And I think in the new age now with AI, in some sense, it's easy to get results. But I think what we have to teach as faculty, professors, is what is a good result and what's kind of a not so useful result. And that's a matter of taste, right? In terms of like what is actually giving you deeper insight into a problem as opposed to just some simple incremental advance or some very simple combinatorial kind of connection. So I think that's actually the hard thing to teach is, where you should really push and have a little intuition in terms of that this result will really lead to some really broad new category as opposed to just, taking your knowledge tree and just kind of incrementally pushing out 1 or 2 nodes. I think if you can really build kind of a whole new tree, that's the type of best results that you get.
I see. Oh, yeah.
Actually, I was going to ask maybe my fellow faculty. I think one of the challenges that we constantly stress about or go with, again, to relate to what no one was saying in the scientific session, is how to think about as a student chasing those new trees or those big, high risk, high reward things. Because at the same time, as a student, you only have so many years in graduate school. You are looking to get a job and feed yourself, and so there's also this very real pressure to generate any results that land in some conference, just so you can say, hey, I'm capable of doing science, and to get that job and you get the promotion. There's a built-in incrementalism to the system that is squarely against doing the original groundbreaking science. That in some ways is what makes science itself exciting. I'd be interested in hearing how you deal with that.
Okay, so if I understand correctly, then in the era of AI for science, then to make students or employee more exciting or motivated, the role of the leader should be becoming more and more important, I guess, to make it motivate. Okay, great. So I think we have about 20 minutes left for the panel discussion. We can actually continue this kind of discussion based on my question, but still, this is now this is also open for any question from the audience. So, yeah, maybe I can ask if we do have any question. Please actually come up and ask any questions from audience or students. Yeah, there is. Okay.
Thank you for great insights. So all of you stress the importance of prior knowledge and the data, helping the search space more confined so that we can produce valid results or valid hypotheses. I also agree, and I think they are equally important, but there's one thing I think we are missing here. If any of you are more or less same age as I am and studied in Korea, maybe you may remember this thing from biology textbook. Our tongue has a specialized sensors, and at the tip of the tongue, we taste sweetness. In the middle of the tongue, yeah, we taste bitterness or something like that, right? I remember this because we were forced to remember all those things. But after 20 years and 30 years, it's wrong. So sometimes our prior knowledge could be directing towards wrong hypothesis or wrong result. So in some sense, when we talk about AI for science, we should also work on something that could refute our prior knowledge, right? And do you know any work?
But then that's the gist of science, right? You have a sort of a principle or a theory. If that's refuted by further observation, that theory has to be modified. So that's the part of, the essence of science, I think. So this prior knowledge is a moving target, right? So I don't.
That's the question of which theory can we take it as truth and search for hypothesis, or which prior knowledge is unreliable and refutable. And the system for AI for scientists should be able to.
Yeah, that's a hard question, but there is, I believe, in a research community, there is sort of a consensus on what's believed to be true at that time, at least, right?
Kyung, I think your question is also a question about, the prior knowledge. At what level of hierarchy or abstraction do you actually build that in, right? So as you said, kind of this knowledge of the tongue having these different zones. I think obviously, as you said, it's scientifically proven, but obviously the tongue does sense taste. And the taste, people know that there's olfactory or sensory receptors on the tongue that do the chemical sensing. So there are things that they should be built in, but maybe at that level of, sweetness versus saltiness on the tongue is incorrect, right? I think that's what takes human knowledge in some sense to know what to put in and what not to put in. I can give you another example, I think, of an interesting prior model that is maybe not useful for AI and for science. So for instance, I know in manipulation tasks, our prior knowledge is the way you should do a manipulation task is you model the friction cones, your contact angles of how a hand holds something. That's kind of our model of how physical interaction with friction and with slipperiness, all those things should be done. Now, there's no model. We don't even have a good simulator for that. right? We don't have realistic simulations, and so we can't really train systems based upon the real gap, right? Especially in robotics. So, what should we put into a machine learning model, AI model that could solve that problem? Still an outstanding.
Okay. Any question from the audience? The back.
Thank you for great discussion. So I have a question. So Professor Lee actually answered back like what professor like expect from the good students and told that like surprise the professor that AI cannot. So upon that, so I want to ask, how can we like build up on that kinds of things like daily habits or like practice on research or like in a better way to like improve that creativity to surprise the professor that AI cannot.
I mean, I think this is a big debate in the whole academic community right now. Is how we train future students properly. What's the kind of standard curriculum of learning to code, learning certain math types of skills. Is that really necessary, or is it more now becoming multimodal, interdisciplinary? So how do you train students that can thrive in that kind of environment? So I mean, I don't know of anyone in the academic community. We're all trying to figure that out. But I do think there will always be a premium on students who can think deeply about something to give insight into some problem that at the surface level looks one way, but at kind of a deeper level they find some connection that is not in kind of any paper right now. That's
Yeah, I kind of agree with it too. I think maybe to me, especially in the AI scientist era, especially students who bring in the context maybe from like other fields or especially like completely other disciplines, that those really like long range connections, which are for me something that I thought of or heard of, something that maybe an AI model, which is just doing some similarity search off of embeddings that are within some distance, would also never find. But those are really kind of cross-disciplinary connections, I think, to me, are where some of the most exciting insights come from, and where some of, for me, the most exciting interactions with students come from, where, like we heard, like, I'm learning as much from the student, if not more.
Well, one operational way to please the professor is try to fail in as many ways as possible. Often the students come, I meet with all of my students at least once a week. And after a week, some students come up with the saying that, oh, I tried this, but it failed due to this and that reason. That's it. We cannot go anywhere from there on. So if you fail in this way, then you might want to try a different approach. And if you fail that one again, you might want to try a different approach. After a week, if a student come up with, oh, I tried this and this, but it failed because of that and failed because of that. Now I'm trying this one. That's the kind of student I like most. So if you know where you are going, which directions are blocked, then your direction will be more evident from that on. So I want students to be more diligent in the sense that try as many failures as possible.
So what kinds of employees do you like most? In that sense?
It's a totally different setting. So I have no idea.
Okay.
Would you like it if your employees failed?
No, to be honest. Yeah.
But I do think that's a great point, that if you look at how we train AI, as soon as you get a failure, you do reward shaping, you tilt away from all those failures. But actually, the biggest insight sometimes comes from failing and then saying, well, why did I fail? You try it again. You find out that if you do this a little bit differently and you understand why you failed, then that actually gives you better understanding of how to actually succeed.
I see. So we had another.
Yeah.
Question?
Hello. Hi. So first of all, thank you so much for the presentations and great panelists. A general question that I have is, earlier you guys alluded that some of the bottlenecks in these frontier models being adopted in the real world being how we evaluate them, the benchmarks that we have. And so I guess the first question that I have is, what kind of ethos should, a graduate researcher as myself and many other people here should adhere to when building these benchmarks, as well as are there any other bottlenecks that are present?
I think for me, benchmarks come up in context of healthcare, and I think especially in healthcare, maybe compared to some other areas of science, we actually have a phenomenal evidentiary base and standards of evidence and protocols for that. And I think to me, we all know deep down how to really assess AI in healthcare. Something that we do routinely in the biotech industry, pharmaceutical industry, and medical devices. Like, we know how that looks. Nobody just wants to do it because it's expensive, it's time consuming, and it really, frankly, sucks to do. And frequently things don't pan out. So I think in many ways in healthcare, some of it's a lack of willpower. Maybe it's also a lack of regulatory muscle to force that to happen. So to me, I think those are the biggest gaps, like in really choosing metrics that actually matter. I think a lot of times, maybe people do choose real-world benchmarks. We did a lot of earlier work in my career in kind of the radiology AI space, focused on like workflow and workflow acceleration and stuff. Important, but ultimately, then what we really want to care about, does this help patients? Does this change clinical outcomes? And again, those are the metrics that are much harder to measure, much longer to measure, much costlier to measure, but they're the ones that really matter. So I think just maybe collectively as a community, building up the willpower to run those studies, I think is what it is.
Okay, so any questions from audience? Any more questions? There are.
Yeah, Eric, just to go along those lines, right? I mean, I guess the question would be, how do we engage more stakeholders early on, even in the question phase, the question generation phase, so that there's some practicality to it, right? I mean, just to give like some examples, when there's this idea or concept about what might be working, for instance, in pre-hospital healthcare, how do we engage the EMTs, the patients, the communities, so that the real questions are actually that we're answering are actually practical and important and useful, and also, that ties into the whole idea of what metric matters, because those communities might actually know more than any of the scientists, and I think that's kind of a component that might be useful to kind of bring in. So I don't know how we can get AI to assist or how to inform that or bring that into these equations.
I think a lot is engaging with those stakeholders. I think to me, one of the most surprising things in the medical space is how little people actually talk to patients about medical AI. There's frequently a voice that's not engaged with, which I think is one of the big maybe shortcomings of us as developers. But again, I do think that if you're building your tools against things that are meaningful in the real world, that's what it's supposed to do. Like, you will find stakeholders who want to engage with you and are interested in running those trials. If people are willing to do the work to set them up. Again, I think especially in healthcare, there's a million reasons to not run a randomized controlled trial. There's regulatory reasons, there's the cost of running it, the time of running it, which all of those things are run contrary to how the AI industry and the tech industry normally works, which is usually with speed, incredible amounts of efficiency, which we just don't have in healthcare. But on the other hand, that's what, especially in the healthcare space, that's what we need. But also, I think increasingly, maybe even outside of healthcare, there's a growing narrative of businesses using AI tools for a variety of business processes and not really seeing a return on that investment. Which again, to me, comes from the gap of our benchmarks, not really capturing the processes that they're supposed to. In some ways, intentionally so, because we build benchmarks to be easy to use and scalable, but we sacrifice validity sometimes for that, and I think that's the wrong design choice.
One point about benchmarks, I think it's easy to make a benchmark or metric for a particular skill. But if you think about it, we don't even have a good benchmark for what makes a good graduate researcher, right? We have qualifying exams, right, which are basically skill tests. But doing well on a qualifying test doesn't mean that you're going to be a good researcher. So actually, we don't even have a benchmark for humans. How we should try to think about better benchmarks for both humans and AI.
Which that is, I think, one of my favorite AI for science papers, which we're probably all familiar with, is the David Ha's work with Sakana one. I think to me, there's a lot of things to say about the Sakana work, but my favorite part is they actually took the papers and submitted them to an ICML workshop, which for scientists really is the real world proof of it. But again, like part of the problem with that is it sucks. It takes time to review at a conference. But to me,
Probably reviewed by other AIs now.
Yeah, but it was great to see someone actually do it.
So,
I mean, my question kind of plays back into your last comment about, reviewing everything by AI at this point, writing everything by AI, reviewing by AI. How can we ensure sort of the scientific method is actually ensured? And I mean, the scientific method itself stands, but I think we should also remember that it evolves how we exactly test a hypothesis. So I know this from my original PhD in physics. We also had to increase basically the discovery threshold at some point. Scientific method stayed the same, the physics stayed the same, but basically in the 60s they found hundreds of particles, kind of how we find now hundreds of better models. And then we had to say, okay, we need to increase this threshold of discovery of what is actually a real improvement, a scientific improvement, and not just basically an engineering, maybe luck even potentially in these days. Do you think we need to take some steps in this direction? And what I would be interested to hear what you're doing ideally, or if you plan to do something like this for your own lab, for your own institution, maybe also nationally, because I'm kind of afraid that we're just going to basically publish or perish to kind of absurdum at this point.
Want to start?
I
Please.
can start. I mean, I think it's a great question about the scientific method. But if you actually look into kind of how paradigms are established in science, it's actually not, we want to be very logical that it's a hypothesis, then you experiment proved it, then people accept it, becomes part of theory now, and then that gets built on. But it's more of a sociological phenomenon, right, in terms of how science is accepted sometimes. And it's interesting now with AI agents, in some sense, if the agents are thinking that this is now true, then is that now the standard, or is it now, whereas humans and agents? So I think it'll be interesting in the future, kind of as kind of a sociological kind of endeavor, how science will evolve.
Professor, you want to add something?
Okay. Well, reviewed by AI, there's one good thing about it. You can do it before submitting your manuscript. You can have it reviewed by AI. So that's both good and bad. In a copyright world, using AI, there is this debate about this. For example, some artistic creation, can we say that it can be copyrighted by an artist if this artist uses AI? So there is this huge controversy over this copyright issue. And as for now, the common understanding is that if the creator, even though he or she used AI to create his art, if the degree is not, over like 50 or 60%, that's accounted. So with the scientific manuscript, probably the same kind of rule can be applied during paper generation and also during the review process. The review should not be done entirely by AI. That's just unacceptable. But human reviewer can be assisted using AI, and that can sometimes generate better reviews too. So I think it's the matter of integrity as a scientist to his or her conscience that, I did the review with the help of AI, or AI did the review with the help from me. So there is this distinction between AI-centered, AI doing the review and human doing the review. There is this sort of a trade-off between the two. And I think we cannot entirely avoid using AI during manuscript, writing and reviewing. But there has to be a certain degree of control over using AI. I mean, as a community, we have to be very clear about what we did with the manuscript writing and reviewing in terms of using AI.
I think also for my research group, I know that I think part of the problem too is, as a community, the system we've, backed ourselves into of conferences with these incredibly brutal review deadlines and even worse revision deadlines. I think that's what's kind of driven some of the demand for AI in the peer review process. I'm a journal editor of actually a paper journal, as quaint as that seems. But the review process it has its own issues. The turnaround time is measured not in weeks, but in months, sometimes years. But on the other hand, it's a much more benign review process, which I think is conducive to, if you're a reviewer and you have, months to review it, the authors have months to respond to the reviews, it lessens that pressure to use AI. So maybe some of the solution is just changing how we, as an ecosystem, engage with the literature. Go old school, print.
Anybody want to ask some more? Otherwise, any other question from the audience? As if not, I think we are pretty much end of the session. So we have 3 minutes left. But yeah, I think we need to conclude this panel discussion. But before you conclude, if you want to add something you really want to say, just maybe add anyone. Otherwise, let's thank our panelists for their excellent discussion and also audience for the questions. Okay, let's thank our panelists again.
All right, so the track F session will begin within a minute or so. So please have a seat. We'll start in 2 minutes. All right, so good afternoon, everyone. So welcome to the session Track F, Trustworthy, Safe, and Governed AI. So my name is Albert No from Yonsei University. It is my pleasure to serve as a chair of this track. So today, we are pleased to welcome leading researchers and industry experts who will share their latest research and insights into building AI systems that are trustworthy, safe, transparent, and aligned with human values. Please note that this session is being recorded, live streamed on the official YouTube channel of the Global AI Frontier Symposium 2026. All right, so now let's begin with our first presentation. Please welcome the speaker, Myuhng-Joo Kim, who is the Executive Director of the Korea AI Safety Institute, and he'll be talking about a trustworthy, safe, and governed AI. So please give him a big hand.
Okay, good afternoon. Yeah, my name is Myuhng-Joo Kim. I'm the Executive Director of Korea AC. AC stands for AI Safety Institute. Today, I'd like to talk about the trustworthy, safe, and governed AI. As a starting point for achieving this goal, I'd like to introduce one of the key approaches the Korea AC has been developing since last year. It's called Integrated National Framework for AI Risk. In other words, we also call it the AI Risk Mapping Project. I would like to share our approach to understand and manage the wide range of risks, especially associated with AI risks in a systemic way. What you see here is the evolution of GPT models. From GPT-1 to GPT-3, the number of parameters, as you know, grew rapidly from about 100 million to 175 billion. However, ChatGPT did not appear immediately after GPT-3. OpenAI spent more than 2 additional years before releasing ChatGPT in November 2022. During this period, OpenAI used a method called reinforcement learning from the human feedback, simply RLHF. The goal is to align the model's behavior with human intentions and expectations. In other words, a new startup, OpenAI, spent more than 2 years trying to reduce the many risks associated with GPT-3 before making the technology widely available. at this point, something very interesting happened. Just 2 months after the launch of ChatGPT, Google gave its first official interview to the Financial Times. Google said, we have already developed AI systems that are more powerful than ChatGPT. However, we have decided not to release them until we find a way to control their potential social and ethical risks. This statement caught my attention. One of the world's leading technology companies, Google, delayed the release of AI model, not because it lacks the capability, but because it could not yet fully manage the potential risks. Now, nearly 4 years later, we ask ourselves one question. Have we really gained sufficient control over the potential risks of AI? This chart shows a comparison of performance of various LLMs provided by Google at the time of the interview. As you can see, Google's Lambda scored higher than ChatGPT in several areas, including reasoning, conversation, personality, and empathy. In other words, Google was not behind in capability. In fact, it appears to be ahead. That's why Google's earlier statement is so important. The Google's company was cautious, not because of the lack of technology, but because of concerns about safety and potential risks. However, only 2 weeks after that interview, Google launched its AI model, Bard. In my view, that was the moment when the safety concerns began to give way to the competitive pressure. It also marked the beginning of the AI race that continues today. What happened afterwards was more serious than most people realized. In April 2023, OpenAI launched the bug bounty program. The original plan was to run it for about 3 months. The researchers around the world was invited to find and report vulnerabilities in AI systems. Depending on the severity of the issue, rewards range from $200 to $20,000. However, this program did not end after 3 months. It is still active today. As of last month, the number of rewarded AI-related vulnerability had exceeded 500. This tells us something important. The risks of AI are not a future concern. They are an ongoing reality today. However, there was some risks that are not eligible for bug bounty rewards. Please look at the items that OpenAI itself excluded from the reward program. 2 well-known examples are jailbreaks and hallucinations. These risks can be reduced, but they cannot be completely eliminated. They are fundamental challenges of today's AI systems, especially transformer-based AI model. Professor Daron Acemoglu, the 2024 Nobel laureate, Nobel Prize winner in economics, raised a related concern. He argued that AI may not have as large an impact on USA economy over the next decade as many people expect. One reason is that many of AI's fundamental risks remained unresolved. And despite the significant progress in its technology, its potential risks are not declining as quickly as we had hoped. The global discussion on AI safety began to gain momentum with the AI Safety Summit at Bletchley Park in the United Kingdom in 2023. Since then, AI Summit have been held in Seoul, here, Paris, and most recently in the New Delhi of India in February this year. Following the UK's example, several countries have established AI Safety Institute, simply ACIS. Today, this institute work together through an international network whose name is NAMES. Here is the full names of Network of Advanced AI, Measurement Evaluation, and Science. AI safety is no longer a challenge for us and a single country. It has become a global challenge that we must address together. The Korea AI Safety Institute was established in November 2024 as the sixth institute in the world. What makes Korea AC unique is that its mandate and organizational basis are explicitly defined. The Article 12 of the Act assigned 7 responsibilities to our institute. The very first responsibility is to identify, define, and analyze AI safety risks. The AI Risk Map project that I will introduce today was launched to fulfill this first responsibility. Before moving to the main topic, let me briefly explain the 3 key concepts: risk, safety, and security. As shown in this figure, AI safety is the broadest concept. Its goal is to protect people from AI-related risks and maintain the trustworthy AI environment. Within AI safety, we identify 3 major categories of risk: AI malfunction risks, AI misuse, that is malicious risks, and AI systemic risks. Especially, AI security focuses on threat and vulnerabilities. These are special cases of malicious risks. And on the top of AI security, we have AI national security concerns. This framework is based on the International AI Safety Report published by UKAC. Let's take a closer look at these 3 categories of risk. First, AI malfunction risks. These include reliability problem, bias, and loss of control. Second, AI misuse, that is malicious risks. These include fake content, manipulation of public opinion, cyber attacks, and CBRN threat, that is chemical, biological, radiological, and nuclear risks. Third, AI system risks. This includes impact of on the labor market, gaps in research and development, market concentration, environmental issues, privacy concerns, and copyright challenges. This classification is also based on the International AI Safety Report, which was first published in last year and updated this year. At this point, you may ask, are we the only ones working on AI risk classification? The answer is no. These are already several excellent efforts in this area. One of the most important examples is the AI risk repository developed by MIT. This is the large-scale meta view that integrates 74 existing AI risk frameworks and taxonomies. It identifies and organizes more than 1,700 AI risks. In terms of risk classification, this is one of the most comprehensive efforts in the world. AIR 2024, this study takes a different approach. The researchers analyzed 8 government regulations and 16 corporate AI policies from United States and European Union and China. Based on this analysis, they identified and organized 314 AI risk categories. This risk was then structured into 4-level hierarchy. In other words, AIR 2024 focuses on how AI risks are defined and addressed in real-world policies and regular frameworks. The next two examples are different. They are databases that record real-world AI events and cases. The first is OECD AI Instance and Hazard Monitor, simply AIM. AIM automatically analyzes news reports from around the world and collects AI-related instance and hazards. Importantly, it distinguishes between two concepts. An instance is a case where actual harm has occurred. A hazard is a potential risk that have not yet caused harm, but could do so in the future. Today, this database contains about 15,000 recorded cases. This makes AIM one of the largest sources of real-world AI risk information. Another important example is AI Instant Database, simply AIM. AIM is one of the best-known catalogs of real-world AI harm instance and is operated by non-profit organization. Currently, it contains about 1,366 instances documented across 5,499 reports. The number of reports is large because a single instance is often covered by multiple sources. AIM serves 4 main purposes. First, it helps prevent the same mistakes from being repeated. Second, it provides a structured way to define and document instances. Third, it applies multiple classification frameworks to analyze instances from different perspectives. And fourth, it is an open platform where anyone can contribute information. One particularly useful framework is the GMF classification. It helps trace the technical causes and failure mechanism behind AI instance. Now, let's look at these 4 efforts together. MIT's AI Risk Repository and AIR 2024 are taxonomies that classify AI risks. The OECD AI Instance and Hazards Monitor and 8 are databases that record real-world instances. All of them provide a valuable foundation for understanding AI risks. However, they share 3 common limitations. First, they are largely static. They provide a snapshot at a particular point in time, but they do not effectively track how risks evolve over time. Second, causes and impacts are separated. There are no clear paths connecting why a risk emerges to what consequences it may create. Third, and perhaps most importantly, they do not identify who should respond. They classify risks and record accidents, but they do not tell us which stakeholders should take action. This is the gap that our AI risk map seeks to address. If we look at these gaps from the perspective of risk response, they can be summarized into 5 limitations. First, they are instant-driven. In most cases, analysis begins only after harm has already occurred. Second, they are technical and administrative silos. Risks are often treated separately by technical domain or government agents without a unified framework. Third, they struggle to provide early warning. Reactive approaches are not well suited to identifying emerging risks before they become serious problems. Fourth, they are disconnected from security frameworks. They are not fully integrated with specialized defense systems, such as those used for CBRN risks. And fifth, they have a limitation visibility into cascading risks. They may miss how a single failure can trigger a chain of consequences across multiple systems. This limitation suggests that we need a more dynamic, integrated, and action-oriented approach to AI risk management. And this is why we chose a risk map rather than simply classify them. Our goal is to move from classification to governance. The AI risk map addresses these gaps in 3 ways. First, the dynamic tracking. Each risk is associated with a time step and a severity level. It is not a statistical snapshot. It is the living map that evolves over time. Second, a connected pathway. The course map flows into the impact map, creating a continuous link from the origin of a risk to its consequences. Third, clear accountability. On the impact side, responsible agencies and stakeholders are explicitly identified. This project is not simply a research project. The Article of 32 of Korea AI Basic Act requires the identification, assessment, and mitigation of risks throughout the entire AI lifecycle. The Act requires life-cycle-wide risk identification. That is exactly what the course side of our risk map is designed to provide. In other words, the map helps turn legal requirement into practical implementation. And finally, let me emphasize one point. We are not regulators. We are Sherpas helping others navigate the path toward a safer and more trustworthy AI. So one methodology is behind the AI risk map. Its foundation is morphological analysis. This method was developed by the Swiss astrophysicist Fritz Zwick. He is also known as one of the first scientists to predict the existence of dark matter. The core idea is quite simple. The complex problem is broken down into several independent dimensions. For each dimension, we list the possible values. Then we examine all the combinations created by their intersections. As a result, all possible cases can be explored within a single structured framework. The process consists of 3 steps. First, identify the key dimensions. Second, define the values for each dimension. And third, place known risks or cases at the appropriate intersections. This creates a systematic map of a risk landscape. This method is particularly useful for risk analysis for 2 reasons. First, it provides a clear positioning. Every known risk can be placed in a specific location on the map, making it clear to identify, compare, and track. Second, and perhaps more importantly, it helps us discover the unknown. Empty cells may point to risks that have not yet been identified or even named. In addition, this approach offers 3 important benefits. It supports completeness. It helps structure problems that are difficult to quantify, and it provides traceability over time. In fact, these ideas are closely related to Messi MNC principle behind our risk map. Each dimension is designed to mutually exclusive, while the overall framework remains completely exhaustive. In other words, the categories do not overlap, and together they cover the entire risk landscape. Now, let me show you the overall structure of AI risk map. As you can see, it consists of 2 connected cubes. The cubes on the left focuses on causes and prevention. The cubes on the right focuses on impacts and response. The cost cube has 3 dimensions: risk actors, the AI life cycle, and the area of deficiency. The impact cube also has 3 dimensions: the types of harm, affected AI principles, and responding government agencies. A risk case begins in the cost cube and flows into the impact cube. In other words, the map connects causes to consequences. Let's now look at each dimension one by one. Let me simplify it even further. The left side is about cost analysis. Who creates the risk when it occurs, and why it happened. The right side is about impact analysis. What is affected, which principles are violated, and which government ministry or agency is responsible. A single risk case connects these two sides. Just as a river flows from its source to the sea, a risk flows from its cause to its impact. This connection is the core idea of AI risk map. Let's begin with the first dimension on the left side, risk actors. The key question is simple. Who brings about the risk? We identify 4 types of actors. First, ordinary users who create risks unintentionally. Second, malicious users who intentionally misuse AI. Third, tool-based AI systems that act as an instrument under human control. And fourth, autonomous AI systems that can act on their own. This category includes agentic AI. Why is this distinction important? Because different actors require different responses. For example, if the actor is a human user, we can provide education and preventive guide and sometimes penalty. If the actor is an autonomous AI system, we can develop safety and deployment guidelines in advance. Human in the loop is more important in this case. Once we understand the source of the risks, we can design a more effective response, including prevention. The second dimension is AI lifecycle. The key question is when the risk triggered. We divide the lifecycle into 4 stages: design, development, deployment preparation, and operation and rollback. Even the same risk may require different actions depending on the stage where it originates. It would also like to highlight the importance of the rollback. I would also like to highlight the importance of rollback. The ability to safely withdraw or roll back on AI system after deployment is itself an important element of AI safety. That is why we track risks across every stage of life cycle. By doing so, we can better understand where risks emerge and how they should be addressed. The third dimension is the area of deficiency. The key question is where or what is the root cause of the risk? We identify 4 areas. First, deficiencies in technology itself. Second, situations where the technology works, but society is not yet ready to accept or adapt to it. Third, regulatory gaps that allow risks to grow. And fourth, weakness in the industrial ecosystem that limit our ability to manage those risks. I'd like to emphasize one important point. Many AI risks are not purely technical problems. To understand them properly, we must look beyond the technology itself. We must also consider deficiencies in society, policy, and broader industrial ecosystem. Now, let's move to the impact cube on the right. The first dimension of the dimension is the type of harm. We identify 5 categories. First, the physical harm. Examples include accidents, involving autonomous vehicles or failure of medical robots. Second, economic and systemic harm. Examples include AI-enabled fraud and the large-scale disruption caused by automation. Third, social and cultural harm. Examples include biased hiring algorithms and targeted hate content. Fourth, cognitive and informational harm. Examples include deepfakes and large-scale misinformation campaigns. And fourth, violation of rights. Examples include the misuse of facial recognition technology and data breaches. These categories helps us understand not only where risks comes from, but also how they affect people and society. Let me briefly explain the remaining two dimensions. The first asks which AI ethics principles have been violated. And the second asks who is responsible for addressing the risks. We use 5 AI ethics principles. The first 4 are public good, accountability, controllability, and transparency. And these are based on the Seoul Pact principles that I proposed in 2018. To this, we added the 5th principle, robustness. Robustness includes safety, security, and resilience. The final dimension identifies the responsible area of government. We group responsibilities into 5 domains: politics and rights, society and culture, national security, healthcare and public health, and the economic and industry. One important feature is that both dimensions are hierarchical. Ethics principles can be expanded into more detailed sub-principles. Likewise, government domains can be divided into specific ministries, agencies, and organizations. This allows the risk map to become more detailed as needed. Why are these two dimensions so important? Because they transformed the risk map into a living governance tool. They provide 3 key benefits. First, evolving principles. By tracking trend in instant and emerging risks, we can identify and highlight new ethical concerns in a systematic and measurable way. Second, comprehensive coverage. Every risk that affects citizens can be linked into a responsible government body, creating a more complete safety net. Third, an annual AI safety index. The risk map can serve as a foundation for measuring the state of national AI safety ecosystem year by year. In short, the risk map moves us from classification to accountability. The responsibility dimensions transform a map of risk into a map of who is responsible for protecting citizens. But does this risk map actually work in practice? To answer that question, we conducted a large-scale pilot study. We applied version 1 of risk map to MIT's AI risk repository. They included all 2,176 recorded risks. We also compared our result with real-world cases from OECD AI instance and hazard monitors. The pilot confirms 3 things. First, efficiency. Using LLM models, we automatically classified all 2,176 risks and mapped them onto our 6-dimensional framework. Second, accuracy. The automated classification was reviewed by experts and cross-checked against real-world instances. Third, scalability. Our framework was able to accommodate MIT's 74 different frameworks. However, the pilot revealed something even more important. The map works, but it was built on 2 assumptions. First, that risks are relatively static, and second, that risk originated from a single AI model. What we found was different. Many risks evolve over time, and increasingly they emerge from interaction across the entire systems rather than from a single AI model. This insight led us to rethink the next generation of risk map. This is why we are now moving toward the version 2 of risk map. The unit of analysis is changing. Version 1 was designed to map risks at the AI model level. But since then, agentic AI systems have emerged rapidly. And in the nearest future, we will also see the widespread deployment of physical AI systems. As a result, we need a new structure. In version 2, the cost cube can be repeated multiple times. The first cube captures risks originated from the AI model itself, and second cube captures risks that emerge from the agentic systems built on the top of that model. The impact cube on the right remains the same. This approach allows us to distinguish the responsibility of model providers from those of system operators. And when physical AI becomes more common, we can add another layer of cost analysis. No matter how many layers of cost exist, the impacts experienced by citizens ultimately converge into a single impact cube. That's our anchor, public safety. This risk map will never be truly finished because AI itself never stops evolving. Finally, let me share 3 future directions. First, from mapping to measurement. In version 2, we plan to quantify both severity and likelihood using structured scoring methods. The result will be visualized through risk heat maps. Second, from pilot studies to integrated response, we will take a deeper look at high-impact domains, including CBRN risks. We also aim to connect risk scenarios to early warning and response mechanisms. Third, from the national security to global collaborations, we will work with our partners on shared scenarios and joint evaluations. Together, we hope to build a stronger governance for AI safety and security. This project is still evolving. Just as AI continues to evolve, the AI risk map evolves with it. We will continue to remap the changing landscape of AI and its risks. And we look forward to making that journey together with all of you. Thank you very much for your attention.
All right, so thank you for the amazing talk. So we now have a couple of minutes for a few questions. So want to take, sure. Thank you. Any question from the audiences? All right, so like if not, I would like to ask a simple question. So it seems this AISI we have one, Europe has one. There are different ACs all over the world, and it seems like you're having a meeting annually or more regularly. Recently in India, so like, is there any some standard things or like sharing the information between all these different ACs around the world?
You mean the standard way to sharing the information?
Right. So like
right.
So like forming the risk or forming the like how to defend or regulate it.
Not yet. But at this time, the bilateral collaboration is encouraged. For example, Singapore AC and Korean AC is endeavoring to evaluate the security and safety of agent AI, and UK and USA and Korean AC is endeavored to find the CBRN risks. So there is no standard way to sharing or making some common effort. But at this time, we are coupling two ACs. Yeah,
right. Thank you. And any other question from audiences? If not, so let's thank the speaker again. All right, so the next is the panel discussion. So please welcome our panels. So first we have a Jinhwa Ha from Kakao AI Safety Senior Manager at Kakao. And also we have a Professor Pascal Coupart at University of Waterloo and Vector Institute. And also we have a James Petrie, who's the Compute Security and Governance Lead at the Future of Life Institute. And we have a Professor Stephen Eujong Hwang from KAIST, and also Professor Jessica Choi, also from a professor from the KAIST. So please have a seat. All right, so thank you for joining us. Actually, we have way more times than I expected, so I think we have plenty of times. So I think why don't we just start introducing ourselves? So for me, I'm Albert No from Yonsei University. I'm all working on the some theoretical sides of the machine learning, but recently I'm interested in the some trustworthy, including the privacy, safety, and what's the problem, and how to solve it. So that's me, Albert, and please.
Hello, I'm Jin. I work with Kakao, and I'm currently taking 2 positions at the same time at AI communication and also AI safety. My personal interest lies in integrating human rights perspective into AI sector and digital in general, having background in United Nations before. Thank you. Nice to meet you.
All right, my name is Pascal Coupart. I'm Research Director at the Vector Institute and also a professor at the University of Waterloo. In terms of research related to safety, so I've done a lot of work in the past on constrained learning. So this was in the context of autonomous driving, but then also extending this to applications in the context of multi-agent systems.
Hello, I'm James. I actually did my PhD at Waterloo, but did digital contact tracing and privacy preserving apps. For the past 3 or so years, I've been looking at compute governance, so ways to reduce extreme risks from AI by enforcing, preventing bad actors from using compute or verifying how other actors have used compute.
Hi, I'm Stephen Hwang. I'm an associate professor at KAIST. My research interest is data-centric responsible AI. So I'm originally a database person, so I like working on anything related to data. So I've been working on how to solve responsible AI issues in traditional machine learning, including fairness, privacy, robustness, and explainability. And my goal is to kind of sort of support all of them holistically, starting from the data. So machine learning is not just about model training. It's it starts from the data. You acquire data, then you do all sorts of things like labeling and augmenting and so on. So currently I'm extending this research to LLMs, agentic AI, maybe physical AI in the future, and so on. Thank you. Nice to meet you.
Hi, my name is Jessica Choi. For somehow my name was appear in the previous section when people say Professor Choi, and this AI translate as a Choi Jessica Choi. So I was in the audience, but somehow I'm honored for the AI model. So I'm very interested in something like such hallucination and mechanical understanding of those LLM. And I'm a professor of KAIST and the director of Explainable AI Center for 8 years. And also I'm CEO of a startup company called Iniji. And my company is doing AI autonomous operation of mission critical system in the manufacturing domain. So my client typically say why your model was not really correct, and please give a correct explanation how we can fix it. So that I'm using a lot of these explainable AI tools and algorithm to improve those AI models. So of course, this a nice presentation from Myuhng-Joo, and so I also agree that the AI agent and the safety and the security issue of those AI agents, including LLM and the Claude and all of those systems are really important. So I wish to have a good discussion today.
All right, so thank you. So in this panel discussion, we'll be discussing about the broadly speaking AI safety and governance, and like how should we react? What are the problems? So I prepared some topics by myself, but like it's very biased towards my research interest. So since we have a lot of experts in different field, industry, academia, and also the startups, so just feel free to bring up any new relevant topics if you think that's necessary. Just let me start from the topic that I prepared. All right, so the first topic, first question I would like to ask one by one, all of you, is basically how should we handle or treat this safety issues? So for example, like a few years ago, when people say the AI safety, that's more about like a model safety, like how we train the model safely, how let model answer in safe manner. But now like we have agents, right? So like agent, like then the problem becomes how should we handle agent safely, control agents? And now we have the AI labs, like the some multiple agents, and also we have harness engineering type of things. So in this under this type of circumstances, like so the question is, what is going to be the risks in this current situation, and also like who is responsible for this and who should handle this type of risk? For example, the answer can be like the model provider, service provider should take care of this, or like the government can regulate it, or user should handle this appropriately. All right, so I have no answer about this. So like just it's a super open-ended question. Just share any interesting thoughts regarding this issues. So let's start from Jin.
I don't have answer for this, but I think now that you mentioned, it's no longer just model-based. I think AI agent, AI model, AI system, they tend to have different risks, and these kind of risks will have to be tackled simultaneously. I think how, for example, for models, we have Kanana lineup, like Flag or multi-model, Essence. So we have different Kanana models, and for the model safety, we go through empirical, like data-driven, more of evaluation, so that we ensure that the AI models are safe. And last year, we also co-developed with TTA and KAIST the AI safety evaluation framework data set, and I think this actually gives you an idea how it's actually going through an R&D and research related to the model safety area. I think in terms of agent, it's a little more interesting because it no longer is only about the result of the AI, but it's more about the trajectory. And we recently released this WUPI. I'm sure you've heard of it. It's a national secretary for the civic service, and this is for the society. And for the agents, I think it's to ensure the safety of agents, it's important to see the trajectory rather than just a result, and also how it's going to be used and the social impact. For the system, I think in a way it should be more systematic and widely applied as a group. And Kakao not only works in its own manner, but it interacts with different affiliates. And as a group, we run a committee level dialogue on a regular basis, and we work on AI ethics principles and checklists. It's more like a risk pre-screening process. So I think we should actually have multi-layered and perspective in terms of dealing with different AI system or agent or model risks. So I hope it answered.
Yeah, so among the three different levels, I would argue that system is by far maybe the most challenging one, and perhaps the one that
going forward, people are going to have to invest a lot more effort to prevent and come up with ways of I guess, managing the risk. So maybe as a concrete example, so one colleague at the Vector Institute, Nicolas Paterno, recently showed with his lab that you can develop some worms that will replicate and so on, and in fact, using various vulnerabilities. These don't even have to be zero-day vulnerabilities, but they can be discovered and so on. And then it's in part because now we have systems, multiple agents that can work together and essentially discover these things in a way that's a lot faster, a lot more comprehensive, and so on. But ultimately, like systems of many agents can do things that maybe the creators cannot even think about. So therefore, in terms of risks, in terms of possible attacks, there's, we can't predict what this will be, and we're really, entering a new era here. So I think there's something very risky and fundamental that we need to explore here.
Yeah, that sounds scary, but yeah. All right, so James?
Yeah, I think I'm most concerned about the dangers from the most capable AI systems, which I guess is a different use of the word system. But so I think I would focus on the development process and internal deployment of the newest AI models. And so especially around, I think a lot about compute. So verifying or preventing bad actors from getting compute and verifying how compute is used as one of the more robust sort of safety nodes.
Yeah, so I think the question is like whether we should be like focusing more on the model or agentic AI and system. And I don't think I think all of them are really important. And I agree that system and agentic AI are really complicated because it's kind of like beyond the model, and you have to be kind of build a whole ecosystem that makes sure the model is not misbehaving and so on. And so I totally agree with that point of view. I also like to mention that I think making sure the model itself is safe is also still important. So one example is nowadays there's a lot of personalization going on, and one of the research I'm doing with my students is if you personalize the model too much, it becomes very psychopath. It like kind of always says you're a genius and you're very good, and people feel very good about that. But it's very dangerous, right? So it could lead to people just talking to these chatbots and feeling good about themselves. So there's definitely some danger out there. There are many ways to also poke other holes as well. So I have another research where if you kind of change the phrasing of a prompt, then a model that used to be fair suddenly becomes unfair. And so we have this paper in ACL in a few days. And so the models are not like perfect right now themselves. They still need to be improved a lot. So I just want to mention that it's still very important to look at and improve the individual models in addition to like the systematic, solving the systematic issues as well, which is very important.
Yeah, so I also agree with other panelists. And the model is one of the most important parts because the important information such as privacy information is stored in the model. And when they combine new risk of those information, and sometimes as we actually appear in the mythos, and when they create a new risk factor to threat our society. So in that sense, actually, like as I on research of explainable AI, so it is very important to like understand which information is like stored where and how we can handle those and turning on and off, and so how they are react and so on is very important topic. But in this actually scenario, so I little bit afraid that whether we can control those information stored in the model and also in the era of agent, because so not all models are like generated by the public sector, including the university. So there are a lot of private sector competing each other, And somehow, if we regulate like learning the model, then somehow we are reducing the performance of those and the monetize of those private companies, something like big tech, are hampered by those regulations. So I'm not so sure. So in the actually like a big, like the countries who has a big regulation has a better like LLM model in a way that, so I'm a little bit afraid that, so whether like big good regulation for the model and the agent can improve the like how can I say ultimate the safe or trusty AI model and so on. So in a way, so I actually like think about the good question that Albert say, and probably in the system level would be the one of the options. So somehow, as an example, so in South Korea, so of course actually South Korea is just a normal people, but we have a lot of CCTV in the public space. So if you're doing very bad, then this tracking system eventually can find you when, where, why, and like doing bad thing. So that people try to avoid those actually bad behavior. So what I'm saying is, we can make those safe system in our daily life of AI use. So if we agree that, so it is actually a little bit different, like how can I say, so we need to like clarify which one is open space, something like open space in terms of location, and which space is good for our open location in our like internet AI LLM like era. So then if we define those well, then we can have a lot of safety tracking agency, whether some of the private information were like hacking or threat information is go through, and the finding and the report and the share and the track to find the who actually do the bad thing, how we can like prevent those is one of the actually the system level prevention is at least we can do in the Beijing level. Of course, actually we should do in the model level, in the agent level, but somehow in the competition of the AI performance and the monetization and like a regularization of those AI maybe not so like a practical, so that would be we can have a good system level protection is what I think.
Yeah, thank you. I mean, like, I agree because, sure, so like in terms of the explainable AI, we need to understand model better. But like at the same time, we have almost no idea like why LLM is working, like why LLM has this AGI level performance. So like we have still limited understanding about this model. So I agree that maybe controlling the usage is maybe the better part. Thank you for the comments. All right, so now, so second topic is also my interesting, based on my interest about the unlearning. So the unlearning, I think like many of you are already familiar with. So it's starting from the some privacy concerns. So like your language model trained on some like a web crawl data, which may contains your information. And also a lot of time language model trained on the unauthorized copyrighted data, such as New York Times article or Harry Potter book or something like that. So like there also are like a lot of the ongoing lawsuits, and also there is a European act called the GDPR. So the one solution is called machine learning. So of course this is not gonna be the only solution. So to let a model forget about certain information like copyrighted information or some private personal information. So my question would be more generic. I mean, like, of course, if you want to say anything about the unlearning, that's fine. But like, it's kind of problematic, right? So like, is LLM is okay to train on your personal data without your authorization? Or is it okay to train your model on the some publicly available but still copyrighted data, like the articles? I mean, there is an argument, including the fair use, et cetera, et cetera. And once, let's say, if the GPT, let's say 5.5 is trained on your private data, like what should be the solution? Should we let model forget about it, or should we retrain it, or is there any other solution you can think of? Just feel free to share with the audiences. Yeah.
Well, if I rephrase your question, if I understood it well, so we are talking about machine learning, and in my understanding, it's like to refrain from specific data dependencies, and your question is whether it's useful or not useful in some cases. I think it could be useful for static risk. So I try to cluster risk into static and dynamic. These days, dynamic risks are appearing more and more. For static risks, for example, IP issues, intellectual properties, or privacy, or rights exploitation, something like that. So, for example, Kakao, as I've already introduced, we have Kanana Safeguard, and it tries to detect and the harmful content. And it does have specific risk taxonomies that I've already mentioned. So I think machine learning could be useful and also significant when we deal with static risks such like that. But if you are trying to deal with more of a prompt injection or leaking or jailbreaking, of course, these are also included in one of the risk taxonomies of the Kanana Safeguard that we have already. But I think runtime monitoring and response will be more and more important as we reach the era of agentic AI, and for that, so I think machine learning, that's my answer. Yeah.
Thank you.
Okay, so I want to take perhaps a strong position, maybe even controversial, and argue that machine learning is ill-posed and perhaps even impossible. Okay, so ultimately, it sounds great because we're saying, okay, if we don't want to have any issue, then let's make sure we can unlearn, and therefore, you know, after that, there won't be any risks and all this. But the reality is that knowledge isn't, you know, separate, and you cannot just say, I'm going to unlearn concept A. Concept A may depend on a whole bunch of other concepts, and even if you manage to forget about concept A, you might be able to essentially re-infer it from all the other concepts. So like as a concrete example, like let's say for my personal information, let's say we want to remove from some public source my age. Well, you can find my picture online, you can find all sorts of other things. You might be able to eventually, you know, predict what my age is. So even if it's removed, unlearned, and so on, it can still be inferred, right? So this is a challenge that knowledge isn't just like an entry in a database. And in fact, we know from a privacy perspective that just doing anonymization is insufficient because you can always combine with other sources of knowledge to infer the information. And so from that perspective, yeah, I don't feel like this is necessarily a good solution, or at least I feel like the problem is ill-posed.
Thank you.
Yeah, I don't work directly on machine learning, but what I've seen it most in the context of is open weight models where you want to release a capable model that doesn't have bio capabilities or doesn't have cyber capabilities. It seems quite difficult to do, and especially if it's a dual use capability where you want it to be good at software development but bad at cyber. It seems just quite hard. I think also what I've seen is that it often is very shallow. Well, it'll unlearn, but then if you if you release the weights, you can fine tune that capability back relatively easily. So I'm not super optimistic about machine learning.
Yeah, so I have a similar point of view. I agree with the previous arguments. So technically, machine learning is, I think, really hard to do. I once wanted to do research with my student, but we kind of gave up. So I think it depends on what you want to unlearn. If this is a specific fact, like what's the capital of which country, I mean, maybe it's possible to unlearn that. But if it's like a broad skill, like being able to, like, I don't know, program in some language, that's a really hard thing to remove, right? So because you basically have to change the entire model to unlearn something. So yeah, it really depends on the specificity of the task. But there are, like, I think some technical solutions. Maybe like the most fundamental one is make sure that the model doesn't train on the sensitive data in the first place. There are also like works, I think, related to continual learning. So if a model keeps on learning as data comes in, it's gonna like forget some information. So maybe you can make it forget some, make it selectively forget some information. I'm just thinking out loud, but maybe you can also like generate like some disinformation that kind of dilutes some information, like differential privacy, and remove that information. So, but yeah, those are not perfect solutions at all. And I think there has to be a lot of governance in making sure that this model is not leaking information. It has to be outside of the model.
So I agree with other like panelists and especially Jong and Pascal. So, but I will not say that actually unlearning is ill-posed, but somehow. So unlearning would be easy. Unlearning is very important problem so to solve, and also, but the unlearning would be easy when we have two assumptions. When a concept is actually like stored in a specific like level, which is not like composite concept, but single level concept is stored in a specific location, and only one concept is stored in the unique location. So the thing is, I will try to explain why this is the case. So somehow, if a specific concept like JASIC is stored in the single location, the single level, and we can go to JASIC and delete it. But somehow, like JASIC is not stored in the one location, but in the several locations, right? Then we need to search through, then find it. So that is actually a typical example when the President of the United States actually changed from A to B, then whether we can find all the place that actually A is place one. And the other one is actually what I probably Pascal would say, and the concept is not like always in the single level. Somehow the complex concept is only appeared when two separate concepts are like combined together. So A is stored there and the B is stored there, and also they are activated and the A plus B is stored. But if we wish to eliminate the A plus B and the A plus B plus C, then there is a really complicated problem where to like slightly like cutting only those parts as we are doing surgery in the cancer and so on, right? So that is actually like one in the technical level of learning is very important, but ultimate level of unlearning is very hard. But another very important one for the unlearning that I wish to say is, so in this would be actually also engineering, but in the social level, I would doubt from the actual question from Albert whether the big tech know which information that they learn. I'm not actually like I'm not saying that the big tech technical level of big tech is low, but somehow we have a lot of data, and we are tokenizing these data. In some sense, actually, all the information, important information, including privacy information and also IP information, are get together in those big model, because as we are rushing for the performance and the monetization. So I'm not so sure whether they are asking unlearning and they can check whether those information is in the LLM, which means that so when they couldn't find actually those proper level, even if actually the information in the LLM, whether when they actually learn, but they didn't know whether actually they are stored in their LLM. So like that is actually also the more important question that we may need to ask to the one who are doing learning the LLM model. So, but that is also a very hard problem because we are not opening up the document when tokenizing. We are just tokenizing the document to the LLM and learn. So that is actually a very important fundamental question too.
Yeah, I mean, yeah, thanks all of you. So yeah, I kind of agree because I feel like this learning, the motivation-wise, is perfect. Like we want let a model forget about some like harmful information, so like unauthorized information. But like the problem itself is kind of ill-posed. I'm partially agree. And also we tried machine learning. Our lab was not gave up, but like we decided instead of working on the research, we wrote a position paper. So like to say something like the problem is not perfectly well defined. So that's gonna be this ICML. So like if you're interested, please step by our poster. But yeah, I feel like unlearning is not gonna be the ultimate solution for sure. I think maybe we'll take some question from audiences after this. Yeah, but like let's move on for the next question for now. So I feel like the third question and the fourth question that I just shared to the panelists is somehow related. So let me just combine them. So like in the very first question, like I was asking about when we, like a few years ago, we were talking about the model safety, and then now we are talking about the agent safety, right? So like that opens up the whole new risk surface kind of things, right? And this year, especially like when Mythos came out, people are all freaked out. Like a lot of researchers are talking about the 0-day thing. And a lot of people are saying like we are all die type of things. And sure, like, so the question I feel like I would like to answer is this safety type of question is very, very, timely question and very important. And it's kind of, I feel like the researchers and the society should answer somehow immediately. So like if you have any thoughts, I mean like some are not disagree. Like some people are saying like that's way too much exaggeration, like they're advertising their model type of things. So I just wanted to ask you about the some more generic thoughts about the current vulnerability of cybersecurity attack type of things. So sure, yeah.
That's a broad question, I think. Cybersecurity of model or agent or in general?
So I mean, sure. So I feel like the question would be with this Mythos level models. So the threat is, I feel like, immediate, and some people are not agree with it. But so the first question is like, what's your thought? Is it like a super, is way too exaggerated, or is kind of immediate threats? And the second question would be like, how should we react as of 2026?
I think it is immediate, definitely. As far as I know, the Department of Commerce also lifted the export restrict of Mythos and Fable 5. So we are allowed to use soon as Koreans within Korea. And I think although this was designed just for the security reason, for good purpose, but hackers can use this, abuse this in a way. So I think it's pretty immediate. And especially it's because it has dynamic risk in terms of unpredictable risk. And when you talk about 0-day and day, it's no longer about the risk that you already know, but unseen and unexpected risk that we'll have to deal with. So definitely, yes, it is immediate, I think, although it's pretty vague because we can't really articulate them into specific results. But as I've already mentioned in the beginning, it's more of a trajectory. So I think it's important to be flexible and also continuous in terms of monitoring and not being too scared and not to be freaked out. And flexible, it's not only the attitude, but I think in terms of diversity too. We talk about ELSI, ethical, legal, social implications. So I think there should be more of a social dynamic and perspective when we deal with these risks. That's my thoughts.
Yeah, so I feel that the risk is immediate. And in fact, I would argue maybe it's greater than we think, in the sense that even if they did not release Mythos and initially, they said, well, okay, we're going to hold back, we're going to make it available to certain organizations so they can prepare themselves and so on. Just the fact that they mentioned it, there's a whole bunch of organizations out there that now know that, okay, there is a way to create certain attacks. They didn't reveal how, but that's fine because people who have similar knowledge now can think, okay, I can do this. And so I bet that at the very moment, there's plenty of organizations with bad intentions that are actually developing their own versions of Mythos. So even if the code is not available out there, the idea now has been planted into the brains of many people, and now we have to prepare ourselves for all of those potential, right? And so it's not going to be just Mythos, but variants of that and evolved and so on by many organizations. So that's on the risk level, but then on the flip side, I guess mythos can be used presumably to discover vulnerabilities before. So at least my understanding is that at the moment it's being used from a defensive perspective. And so to prepare ourselves, I guess, yeah, more work has to be done to develop such systems. So this is always going to be a race between the attackers and the defenders, and hopefully the defenders can remain ahead.
Yeah, I think I agree with that. I think there's a real risk with mythos with sort of day-to-day like banking and everything like that. I'm more worried about domains where it's harder for the defenders to keep up, such as bioweapons, which some of the labs seem to be talking about now. So in general, I'd prefer governance that gives the defenders more time to react, so getting earlier auditing, earlier regulation into the development process, and then trying to build as much resiliency as possible as soon as you know about a risk that's going to be showing up in a few months. And then also on my wish list is building in ways, like more ambitious ways of reacting to very large risks. So if we see something coming in a few months that some labs are predicting, having the option to slow development or having the option to coordinate around not building particular types of models, I think would be very useful to be able to do.
So I don't have too much to add here. I think all the main comments, good ideas came out. So you know, mythos reminds me of like one of my colleagues at KAIST who kind of a few years ago won some DARPA challenge on finding bugs, and his team was using LLMs to do that. So yeah, this is very like effective. I mean, I'm sure mythos is really effective in finding vulnerabilities, and so yeah, I just, you know, I just have a conventional thought that I think it's very important for the software industry to be able to like patch their software quickly, especially for zero-day threats, and for lesser threats. I mean, it has to be still has to be faster in terms of how we can, you know, identify like fend these immediate threats. I think the cycle is going to be much shorter.
Yeah, so I also this event and the threat is very important and the immediate impact to our society, and also there are some interesting phenomena with this. So one thing is actually like, as probably like Pascal may agree, but previously when we talk about AI, so we say that AI is less like competitive because they lack of common sense. And then now we say that like they are less competitive because they lack of physical power. But if you think about cyber security, it doesn't need actually common sense and doesn't need actual physical power. And then in the space, the mythos actually like give us and demonstrate that AI can become a superhuman level power, so that it become a very important threat to the many of those actually like societies, because when one has a method and can attack any of those important systems, right? So that I think actually this is very like ultimate example that when some like assumption and some condition met, AI can become a superhuman power and can treat like humankind and so. So the remaining thing is common sense and the physical power. So we can imagine that in a couple of years, when AI has a good physical power, then they may become the threat to the human. So because they are powerful than the human, and those AI and combined with the physical one, then it becomes the uncontrollable one. And another one that very important one is actually so those the AI capability is asymmetrical. So meaning that previously when US big tech making the AI LLM model and China say that we have a DeepSeek, and then all the other country like EU and Korea actually follow. And then like again the US, one of the US big tech demonstrate that in some constrained environment and the constrained information, something like hacking information and so on, whether they can make the one like a super level AI, and they can control those. So I think actually in that the competition, probably the China, the actually who made the DeepSeek, and maybe actually try to if I'm a Chinese government officer, I would order to the DeepSeek, you should make the similar to the method. And also not only for the China, but all the other country would do that. So, but somehow we are not so sure that is how much this would be easy. So in a way that because of the power and some of the technology gap, and there are big how can I say gap in terms of use of AI, because you US say that we will control those AI system and so on. So another one that also interesting thing is actually I think actually cybersecurity may be very important, and will be a lot of money and the investment going on, at least for the each of country may invest to make the similar one and the methods and so on. But somehow because of AI threat, so many cybersecurity experts become very, how can I say, demanded, and also they got higher salary last year and this year and so on. But eventually what we in the society need is not only for the cybersecurity expert, but also for the AI expert who can make an LLM model, who can substitute some of the cybersecurity experts. So that is actually also very important, how can I say, transition job. The cybersecurity experts should know the AI system to compete in this environment. So that I think that is also very interesting, of course not well organized, but interesting, so that we can think about in the next couple of years.
Yeah, thank you. So yeah, I mean, as Pascal says, I mean, all this topic I motivated by the Nicolas Carney's YouTube talk. So he mentioned about all these new threats, and he also mentioned that yeah, I mean, the whole history of this, cybersecurity thing is basically the attacker versus the defenders. So attacker always finding a new threats, a new leakage, and new vulnerability, and defender finds the patch and how to react this type of issue. But the point of the talk was as James says, it's now way too fast, in terms of with the mythos or any other GPT 5.5 cyber, whatever. So the attacker can do way faster. Even with the same mythos ability as a defender, it's really hard to react all of those multiple threats. And now I think I agree with the Professor Choi. Maybe we need to build a LLM to react this attacks. Yeah, thank you for the comments. So my final topic would be about the agents. So now I keep asking the same question. So these days we have agents, and agents do so many different things, calls the tools and do the job instead of you, and reads your email. And of course, there are some known threats and known vulnerability people are worrying about. And so if you have any specific concerns regarding the agents, or if you have any specific topics that are that need more attention from the society, please feel free to share with the audiences.
I think I wanted to mention this in the beginning, but I kind of forgot. So if you're talking about agent and safety, one agenda that really caught my attention was the human agency, because I read this article that the Pennsylvania sued character AI, and this was about the chatbot and children rights. And I think child rights issues, it's becoming more important day by day as AI evolves faster and faster. So I just mentioned GUPI. It's a National Secretary Civic Service, and Kakao has been deploying. And you can see that Kakao used to be a connectivity platform, but now it's pivoting to more of an agentic AI company. And I think here we need to really think about, and we need to emphasize the significance of human agency And for example, we have this ethics principle that focuses on user autonomy. And by philosophy, we try to argue that this is pretty fundamental when we try to develop service or model. So that I wanted to mention. And one other effort that we are putting is the checklist that I briefly mentioned in the beginning. This is a group-wide thing, and fundamentally we have ASI, AI Safety Initiative, and we try to define technical risk and human ethical risk. And based on this kind of cycle and also the ethical principles, we try to make an implementation tools. And this relates to more of a governance level. It's not just a tool to make safety happen, but to make the whole system, Kakao and affiliates, having the common rule to follow and to make more of a safe governance for AI. So I just wanted to mention all these. And yes, agent safety it does matter. And I think it brings a lot of issues, including child rights issues, hallucination, deepfake, everything. But I think governance really matters more and more. And I just wanted to give more of the examples that happens within the field AI company. Thank you.
Yeah, so with respect to agents, I think there's definitely lots of very, very important risks. I mean, we discussed already many of them, but additional concrete ones could be that they can take actions sometimes that might not look like they're very harmful, but when you compose them together, that can lead to a sequence of actions that then is harmful. And so that's what makes it very difficult to really prevent and detect. Again, if we just look at models and we want to prevent hallucination or prevent deletion of files, these are concrete actions that for sure have a negative impact in just one shot. But then for leaking private information, sometimes it could just be that one agent has permission to access some information, no problem there. But then that gets composed with a whole bunch of other things, and eventually the information gets leaked, right? So this is a challenge that when we look at compositionality, then the space of possibilities, really blows up, and now it becomes really challenging to control that. And I feel like this is an area that's completely open, and as a community, we really have to make progress there.
Thank you. Yeah, I guess for my own use, I use AI agents a lot for prototyping, and I try to sandbox them as much as possible. So separate hardware, isolated from all of my important documents. I think something I'm worried about more generally is sort of systemic risks from agents, where I think we haven't really seen how that will play out, where if it's not a human in the loop, it's just AI agents interacting with other AI agents. I don't think our evals or existing safety frameworks can really predict what's going to happen there. So it's a bit outside of my area of expertise, but I think fairly concerned about what will happen when AI agents start acting autonomously over long horizons outside of sandboxes.
Yeah, so I think this is a very complicated problem. I agree, and I think we need to start start from benchmarking, I guess. So I agree with that. There's no way to I don't think there's any benchmark that can accurately evaluate the risks of agentic AI right now. So even now there are ton of benchmarking works that are published in conferences, but there's still a lot more to do. Also, I think it's very important to make sure these agents have the right authority, I guess. So for example, if for agents that access your personal data that are very personalized for you, there has to be a way to kind of make sure they have limited, can only make limited actions. They can't expose your data to the public and all that. So there has to be some definitely some control. Also, I think you don't want to give too much. I mean, it's the same argument, but you don't want to give too much power to these agents and make sure that they don't like follow any prompt. So you don't want to do prompt injection and make these agents do harmful things without some human that's supervising it and so on. Yeah, so this is a multifaceted problem that needs to be, it's a very open, I agree, it's an open problem that needs to be studied for a while.
Yeah, I also agree with like other opinion, and so I think actually that the risk of agent is not really huge, but I think actually there are many. So that there are many, not so huge, but some risk would be exposed. And there is actually some trade-off between the risk and the convenience of the delegation. So the key is the delegation, how much we will specify you can do or you cannot do. Because it's very convenient to say that, hey, you're doing something instead of me. And then the agent doing whatever they think they are delegated and they're doing something, and there was actually the risk. And then I am not satisfied. Then I will ask to you not doing that way. And then those kind of actually like delegation with some constraint would be longer. And there would be actually some like kind of happening in the future. So we have some example that actually my graduate student at Myuhng do with the Korean broadcasting company. What we do is, so we are making the agents who are purchasing our hotel for the hotel room, and we actually ask them to with a budget of $300 and find the hotel specific day. And we also make a hotel homepage and say that, so if you wish to deeply healing, then you need more than $300, and the 500 would be heal you. And we are asking to individual LLM agent, which agent are hooked by those healing and the purchase more than $300 and so on. I'm not so sure how much you would be mad at 500 or 300 thing and so on. So some people would be really angry about the additional $200, and some people say that of course for family 500 would be good investment and so on. Of course, actually we could say that individual LLM agent with the big tech and the open one has a different level of their own decision to over the budget of the 300 bucks and so on. So what I'm saying is actually that 200 is not really small money, but a small risk, I think, in the a common sense level. But we have this type of question and so on. So as we say, that sometimes money, sometimes our document, sometimes our personal information is going out without our proper delegation or permission. But the agent think, because I need more information or money to do something better, and then they're doing their own way. We find that out the mismatch our intention and the direction, and we're adjusting with several regulation or rule and the one. And that one is, as Jong said, personalized one. So different people may have prefer different the action. So the delegation, how we can conveniently doing those with the communication without much fight with our AI agents would be one of the key. But I think actually those risks may not be really huge, but many. So how we can control, especially Kakao with the big tech, control those issues would be one of the key success factor to go on.
Yeah, I mean, sounds to me like we need some kind of legal contract with the agents and the users. But yeah, I think that's a very tough questions. So I think we have roughly 20 minutes or so. So if any of you panels have any extra topics they want to discuss, please feel free to. I mean, yeah, you want to say something or?
Yeah, sure, happy to. Yeah, I think I would pitch again building policy and infrastructure for global coordination around AI development, which is what I spend most of my time thinking about. I think some of these risks that might show up very soon could be quite significant, and at least having the option to slow down development would be a great thing to have. And so I guess on the technical side, a lot of what I'm thinking about there is around ways to verify what other countries are doing with their AI development. And there's lots of interesting technical problems if anybody is wanting to contribute.
Maybe James, can you give us some examples of like policies or things you could imagine that would be useful here?
Yeah. So I think the simplest one, but maybe less interesting, is around controlling access to compute, which is less of a technical question, more of a policy question right now. We developed some off-switch technology, so there's ways we could develop compute to only run if certain parties had continuously authorized it to keep working. On the verification side, there's a lot of interesting work to do. A lot of what we're focusing on right now is being able to show that a data center is running an authorized model and not doing something else, and to do that in a privacy-preserving way. So we want to show that if you wanted to make agreements about slowing down development, that you could still run whitelisted models. And so we're thinking a lot about trusted hardware that you could put into other people's data centers that could do this in a privacy-preserving way, and zero-knowledge proofs of inference, and lots of other similar ideas.
Yeah, I mean, so I keep thinking like, I feel like it's kind of in the middle of World War type of things. So, I mean, in principle manner, like I agree with the high level concepts, but I feel like it's really hard to control the some individuals, like with the government, because like people are thinking we are at the middle of war and they really, really want to build a nuclear weapon type of things, right? So like any.
Yeah, I think, it's definitely not an easy problem. I think it's important to at least try to have the option. I think I'd feel bad for not trying. But I think there's a lot of shared incentives, I think especially around loss of control and malicious use. I think if countries started to worry a lot more about loss of control risk, there's at least the incentive to cooperate around not creating systems that are like take power. I think that seems very unstable unless they're very concerned, or if we have very good verification technology. So I think a lot of what I'm trying to do is create that verification technology so you don't have to trust other parties.
Sounds to me like a nuclear weapon thing. So there is some mechanism like where to check whether some country is doing, right?
Yeah, I think a lot of what I think about is around the compute. So showing, like, if you know what compute exists and what it is doing or not doing, then you can make claims, at least at a high level, about large-scale AI development. I think more nuanced claims about like smaller development, it's hard to be like super precise. But I think if we wanted to say we're going to at least slow down for a few months or a year or two, that might be possible to verify, at least like fairly robustly.
Okay. Thanks. So like if you have any other, or we can move to the take some questions from audiences. So thank you for staying with us till this late. So if you have any questions, so feel free to ask to the panelists.
Thank you for the presentation. I was curious about, this topic is trustworthy AI and then governed AI. And we think, the ideal version of it may be one type, but I think sometimes they kind of conflict. And so, for example, the trustworthy AI or safety AI for the company or corporation might look one way, but they might not look the same for the public or the users or individuals. So I was curious, like, when those kind of conflict in terms of interest or the algorithmic kind of approach, or just a cost effectiveness, how do we think about this and how do we approach this?
All right, so I'm a moderator. I'm not going to answer it. It's just so many. So I mean, I can start. Like, I feel like that's not AI specific question. I feel because like it can be the case for most of the technologies. Some technologies, some regulations may work for the company, but not for the public, or the other way around. So I feel like the AI also the same. Of course, like there are some AI specific issues, but in high level view, I feel like AI is also the same. Like we need to get some kind of social agreement on that. I don't feel like there is some specific answer for that. Yes, please.
Yeah, so basically there is a similar problem. So whether we have our own private information that we store, or so we have our so if we have a group or the company has very important their own information, and also country. So especially the public sector, all the public officer use AI, whether we can reveal those information to the big tech. So whether located in the Silicon Valley, so whether Canada or Japan or Korea. So the thing is, in the country level, the sovereign AI is especially very important for the public sector, for public affairs, public information for the country. And they each country try to have their own sovereign AI to store their information safely in their own cloud service and so on. So that, but in the individually, all of our data is stored in the somewhere, like big tech, and we are safe. We feel that those information is safe, and also big tech LLM company actually try to keep those information safely, because if their service is not safe, because the client and user going out to the other more safe one. So I think actually the big tech and those service providers try to getting those information safely in the responsible manner in their way. But even if it's a case in the company level, the country level, it may have a little bit different story. So I'm not so sure what at the end of the story, who will owning those sovereign AI and so on. But I think actually that difference, even if all the technical detail and all the similar, is actually what we may need to think about. Of course, it's because of that, as James say, so even if we are using the good AI service, top 1 to 3, so we also need somehow our sovereign AI one. So then, of course, actually we need to fill those gaps, meaning that those sovereign AI should be improved until these level, and also we should share some of the information. This one is good for the hacking, and good for the responsible AI, good for the performance, and so on. That would be very important issue that we may need to discuss in these two different level of AI use era.
Sure, yeah, please.
I think this is about stakeholder engagement in a way, like public-private sector. I don't necessarily think it's a conflict. I think it's a journey to find a midpoint and compromise. So I think that's one of the thoughts that crossed my mind. Also, I think there should be more of a dialogue about the fundamental concepts, like what is responsible, what is ethical, what is trustworthiness. And I think that involves a lot of stakeholder engagement, again, because every different sector and aspect of society, they would have different views about this. So it's very vague and philosophical area, but I just wanted to add this comment.
Thank you. Any other? Yeah, please.
So I totally agree that there needs to be a better, clear definition of what trustworthiness is. And so for my case, I'm interested in common things like fairness, robustness, privacy, explainability, and it turns out that there are these there are kind of these trade-offs. So if you're very good in fairness, then you kind of tend to sacrifice accuracy because you're trying to make sure that the minority group has the good performance as well, just like the majority group. So also there are trade-offs between fairness and privacy as well, and so it's kind of complicated. So And I think it's not just about like corporate versus user difference. I think in the future, these everyone is going to want like a different type of system. So again, like back to the personalization point, I think these agents are becoming more and more like tailored to users. And my understanding is that there are a lot of there's a lot of technology and startups that try to really make personalization possible. So for example, you need a lot of context. These models have to understand, be able to memorize a lot of context to personalize well. So there's a startup for that. Yeah, I think the main issue is, what are like the pillars of trustworthiness, and like what combination are you willing to tolerate? So it's going to be a very complicated task.
So yeah, I think I hope that answers the questions. Any other question from the audiences? Oh yeah, please.
Thank you very much for an insightful discussion. So when we talk about safety, sometimes safety is not just malicious intent that people have by using the technology, but it's just the technology failing and hallucinating and giving us some random devices. So what do you think some of the necessary milestones need to be achieved before we can trust LLMs in terms of the way people think? We can justify our actions by kind of finding some training data back in our minds or explaining the logic. So what do you think can be important or necessary for us to trust the final model's outputs?
Any thoughts? I mean, personally, I feel like there's no 100% perfectly safe model. Like even human being, like there's no perfect human being, right? So I feel like, for example, like driving, some current level of the self-driving is as good as human, right? But like the question, like, can we trust those algorithms? Is of course no, right? So it often fails, of course, but like the rate is lower than the regular human. But like I feel like it's more like again, social agreement. So like since it's better, so can we adapt it or not? But of course, like we have we need a kind of systematic some evaluation tools, techniques, benchmarks, and also the penalizing systems type of things. Yeah, I personally, I feel like there's no way to 100% guarantee of something. That like I feel like a better answer should be like, how should we build a system with not 100% safe entities, including the human beings? Yeah, that's super personal answer. But any other?
So failures are obviously important to deal with, but I would say by today's standard, it's sort of like a classical problem that the community has worked on for quite some time. Whereas attacks and anything that adversarial, this is more recent and a lot more problematic. So that might be why we did not discuss this very much. But then, okay, to deal with like hallucinations, there are simple non-technological solutions which are as simple as like you get a piece of information, you just go and verify it yourself, right? Like whenever some LLM gives you something, you go and double check, right? And I guess the issue is that people often trust a lot these systems too much, right? And just like when you meet a random person on the street, you don't necessarily trust this person for everything, right? And so we always have to have some, I guess, mechanisms by which we're going to ensure our own safety against failures, against malicious actors, and so on. It's just that now we shouldn't just trust computers in the way that we used to, right? But okay, coming back to maybe failure cases. So there is also a whole community working on constraint systems, so where you can formalize and even learn from data constraints, and then that can help make sure that certain guarantees can be provided, but that doesn't necessarily cover everything, because there's always risks that you don't think about initially, and for which you may not have constraints built in, but otherwise you can at least start from this.
All right. So I think that's a good answer for this question. So any other final thoughts, comments, questions, feedbacks? All right. So we have 45 seconds left, but I think it's good enough discussion to have. So I feel like it's time to say goodbye. So again, thank you all the panelists for this wonderful discussion, and also thank you for the audiences to staying up all this late. We may have jet lags, but thank you again. All right, so that's it for Track F, the Trustworthy, Safe, and Governed AI. And also this concludes today's Global AI Frontier Symposium. Thank you all, and thank you all these panelists. Let's thank the panelists again. All right, so thank you all, and we'll looking forward to seeing you again next year. Thanks.
My
Yeah.